At the very edge of the Sun's reach, a handful of icy bodies move along weird paths. Their orbits tilt, cluster and bend in ways that seem to suggest something massive is tugging on them from the dark. That silent pull hints at a world so distant and dim that our best telescopes have never spotted it. This possible planet, 10 times the mass of Earth and roaming hundreds of times farther from the Sun than Neptune, has been nicknamed Planet 9. If it really exists, its discovery would upend our picture of the solar system and force us to rewrite the story of how planets form and evolve. Let's look at the strange clues it has left behind and explore the bold searches underway to bring this hidden giant into the light. Shadow of the original ninth, Pluto's identity crisis. In the winter of 1930, a young amateur astronomer named Clyde Tombaugh peered through a telescope at the Lowell Observatory in Flagstaff, Arizona, and spotted a faint speck drifting slowly against the backdrop of stars. After weeks of careful study and photographic comparisons, the announcement came: a new planet had been found. The world cheered. For the first time in nearly a century, the solar system had a new member. It was named Pluto, after the Roman god of the underworld, a fitting nod to its dark and distant realm. Just like that, the ninth planet was born. The discovery made headlines around the world. For the public, it was a moment of shared wonder. It was the era of grand exploration, when science and mystery often walked hand in hand. Pluto entered schoolbooks, atlases, and science classrooms as the final chapter of our planetary family. Children learned its name alongside Mercury, Venus, Earth, and the rest. At first, it was thought to be massive. In fact, early estimates of its size were wildly off. When astronomers went looking for what they called Planet X, a large, unknown world thought to be disturbing the orbits of Uranus and Neptune, they expected something big, possibly even heavier than Earth. That's what they were hoping for. That's what the theory predicted. So when Pluto was discovered, it was slotted into that role. It fit the narrative, at least for a time. But over the following decades, as telescopes improved and observational techniques grew more precise, astronomers noticed something odd. Pluto didn't seem to be big enough to account for the gravitational effects they were trying to explain. In fact, it wasn't just slightly small, it was incredibly tiny. Eventually, it became clear that Pluto was smaller than Earth's moon. That was the first major crack in its identity. A planet surely must be larger than a moon. Then there was the orbit. Pluto's path around the Sun wasn't neat and orderly like the others. While the major planets traced out near circular orbits along the same plane, Pluto cut a different line. Its orbit was tilted, 17 degrees off the flat plane most planets followed. Even more strangely, it was elongated. For nearly 20 years of its 248-year journey around the Sun, Pluto is actually closer to the Sun than Neptune. Between 1979 and 1999, Pluto temporarily became the 8th planet, bumping Neptune down a spot in terms of distance. Astronomers found this unusual, but the public didn't seem to mind. Pluto had already cemented its place in popular culture. It had character, it had mystery, it even had a Disney dog named after it, introduced just months after its discovery. Generations of schoolchildren grew up drawing Pluto as a cold, lonely ball spinning at the edge of everything. Its odd behavior only added to its allure. Pluto wasn't like the others, but that just made it special. By the time the space age arrived, scientists were beginning to realize that the solar system was stranger and more complex than they had imagined. The discovery of the asteroid belt had already forced astronomers to rethink what counted as a planet in the 19th century. Now, the outer solar system was offering new surprises. In 1978, another twist emerged. Pluto was found to have a moon, Charon. But this wasn't just any moon. Charon was large, nearly half Pluto's size. The two bodies were so similar in mass that they didn't orbit the way Earth and the Moon do. Instead of Charon orbiting Pluto, both of them revolved around a shared point in space just outside Pluto's surface, a barycenter. This odd configuration, led some to suggest that Pluto and Charon should be considered a double planet. Once again, Pluto was hard to categorize. Throughout the late 20th century, Pluto kept its title. Space probes were sent to study other planets, but none had yet reached Pluto. It remained a distant mystery, unvisited, unexplored. Every now and then, astronomers would quietly discuss its strange nature, but those debates didn't reach far beyond academic circles. To most people, Pluto was still a planet, and always would be. But the scientific unease kept growing. As technology advanced, telescopes began picking up more objects in Pluto's neighborhood, small icy worlds scattered beyond Neptune. The region became known as the Kuiper Belt, and Pluto wasn't alone there. In fact, it turned out to be just one among many. It was still the largest one known, but not by much. The uniqueness that had once set Pluto apart began to fade. The cold, distant world started to look less like a lonely planet and more like a member of a crowd. This slow realization created a quiet shift in the way astronomers thought about Pluto. With each new Kuiper Belt object discovered, the case for Pluto's special status weakened. It was no longer a question of just Pluto's size or orbit. It was now a question of category. What was Pluto really? The world hadn't stopped loving Pluto. But the science was beginning to tell a more complicated story. The planet that had once stood proudly as the ninth world of the solar system was starting to cast a long, uncertain shadow. Why the IAU changed everything in 2006. In August 2006, hundreds of astronomers from around the world gathered in Prague for the 26th General Assembly of the International Astronomical Union, the IAU. These meetings happened regularly, but this one would become one of the most talked about in the history of modern astronomy. At the center of it all was a question that for decades had quietly followed Pluto wherever it went. What exactly is a planet? In the early 2000s, discoveries beyond Neptune had started to accelerate. More objects like Pluto were being found, some smaller, some about the same size, and one that seemed to be even bigger. That one was called Eris. Discovered in 2005, Eris was a rocky, icy body orbiting far out in the solar system, nearly 3 times farther from the Sun than Pluto at times. Early estimates placed Eris as slightly more massive than Pluto. If Pluto was a planet, then surely Eris had to be one too. But the idea of adding Eris, and possibly dozens or hundreds of similar objects, to the list of planets created a problem. The solar system had been stable in the public's mind for so long. 9 planets. Introducing a new 10th planet should have been a moment of excitement. Instead, it triggered a wave of concern. If Eris was a planet, what about the other Kuiper Belt objects being discovered? How many planets were too many? Could the list grow forever? This is what brought the astronomers to Prague with a mission: to define, clearly and officially, what the word planet actually meant. Up to that point, there had never been a formal, scientific definition of a planet. It was something everyone thought they understood, but when pressed to explain it in clear terms, the answers varied. Some based it on size. Others looked at how an object moved. Some included where it formed or what it was made of. Without a clear definition, everything was being held together more by tradition than by science. In Prague, the IAU aimed to settle the issue once and for all. At first, the working group tasked with creating the definition proposed something surprisingly generous. Their draft would have allowed not just Pluto and Eris, but also Pluto's moon Charon and even Ceres, the largest object in the asteroid belt, to be called planets. That would have instantly expanded the list of official planets from 9 to 12, with the possibility of more to come. But the idea didn't sit well with many astronomers. Critics felt the definition was too loose. It didn't take into account how planets interacted with the space around them. Some worried it would open the door to dozens of planets, maybe more. The clarity people were hoping for seemed further away than ever. As the days passed, the debate grew louder and more intense. Scientific arguments blended with emotion. For many, Pluto was a cultural icon. It had stood as a planet for over 75 years. People had grown up with it. It was part of their understanding of the cosmos. To change that felt like erasing something personal. Still, the IAU moved forward. After more discussion and revision, a final definition was brought to a vote. According to the new resolution, for an object to be considered a planet, it had to meet 3 criteria. First, it must orbit the Sun. Second, it must be massive enough that its own gravity pulls it into a roughly spherical shape. And third, it must have cleared the neighborhood around its orbit, meaning it must be gravitationally dominant and not share its orbital space with other bodies of similar size. Under this new definition, Pluto passed the first 2 tests. It orbits the Sun and it's round, but it failed the third. Pluto shares its part of the solar system with many other icy objects in the Kuiper belt. It hasn't cleared its neighborhood. It's not the dominant force in its orbit. And just like that, Pluto was no longer a planet. Instead, Pluto was given a new label, dwarf planet. Alongside it were Ceres and Eris, which also met the first 2 criteria, but not the third. Dwarf planets were still part of the solar system, still important scientifically, but they were officially placed in a different category. Only a small number of astronomers, 424 to be exact, were present for the final vote in Prague. Some critics argued that the number was too small to make such a major decision. Others questioned the timing and process. But the vote passed, and the resolution became the official stance of the IAU. The reaction was immediate and divided. In academic circles, some welcomed the clarity. The new definition gave scientists a consistent framework for classifying objects as more discoveries poured in from the outer solar system. It marked a shift toward understanding the solar system as a dynamic, evolving system with many different types of objects. But outside of the scientific world, the public didn't take it well. The announcement that it had been demoted sparked frustration and sadness. Protests popped up. Letters were written. Campaigns to replanet Pluto appeared on T-shirts and bumper stickers. A group of American politicians even introduced a bill to declare Pluto a planet by law, at least in their state. Some scientists joined the backlash too. Not all astronomers agreed with the new criteria. The cleared the neighborhood rule in particular was criticized for being vague. Some pointed out that even Earth shares its orbit with thousands of asteroids. Others questioned whether the location of an object should matter more than its physical nature. Alan Stern, the principal investigator for NASA's New Horizons mission to Pluto, was among the most vocal critics. He argued that the new definition was flawed and overly narrow. To him, Pluto remained a planet and always would be. After all, New Horizons was set to fly by Pluto in 2015, offering humanity its first close-up view of the mysterious world. To Stern and others, Pluto's scientific importance hadn't changed. It was only the label that had. Despite the controversy, the IAU stuck with its decision. The definition of a planet remained unchanged in the years that followed. Pluto's reclassification was now part of the official record, but in classrooms, museums, and conversations around the world, the debate didn't end. For many, Pluto was still the 9th planet. The emotional connection people had to this distant world couldn't be so easily erased by a vote. The IAU's decision in 2006 sparked a global discussion about science, authority, and meaning. It raised questions about how decisions are made, who gets to make them, and what happens when science collides with the imagination of the public. In redefining what it meant to be a planet, the IAU had drawn a line, not just through the solar system, but through the heart of one of astronomy's most beloved stories. And in doing so, it made Pluto a symbol of how science itself evolves, what Ceres, Eris, and Makemake meant for planetary status. Ceres was discovered back in 1801 by Giuseppe Piazzi. At the time, it was celebrated as a new planet. It orbited the Sun, it moved in a predictable way, and it fit in nicely between Mars and Jupiter. For decades, Ceres held its place among the planets, but then other objects began to show up in the same region: Pallas, Juno, Vesta, and many more. By the mid-1800s, astronomers realized they hadn't found a new planet. They'd found a whole field of small bodies. Ceres was reclassified as the largest asteroid. This episode faded into the background for most people, but it offered a lesson. Planetary status isn't just about orbiting the Sun. Fast forward to the 2000s, and a similar pattern was starting to repeat itself, only this time at the outer edge of the solar system. A team led by astronomer Mike Brown announced the discovery of Eris, and a short while later, he and his colleagues also discovered other distant objects like Makemake and Haumea. These bodies were smaller than Eris but still shared key traits: icy compositions, orbits beyond Neptune, and irregular paths that didn't match those of the classical planets. Makemake followed a highly inclined orbit and had a surface covered in frozen methane. It was bright, cold, and distant, with characteristics that mirrored Pluto's in many ways. Haumea had an even stranger story. It was shaped like a flattened egg, spinning rapidly, and it had a couple of small moons. Its orbit was tilted and stretched. All of these features pointed to a violent past, perhaps involving a collision that shattered it into its current shape. Scientists now faced a choice. They could either expand the definition of a planet, or they could narrow it down, creating a new category that made sense of these small, icy worlds. That debate came to a head in 2006, and the term dwarf planet was introduced. It was a compromise, a way to recognize these worlds without rewriting textbooks to include dozens of planets. Ceres, oddly enough, made a return under this new system. Though it had been labeled an asteroid for more than a century, it was round and orbited the Sun, and it didn't share its space with many other objects of comparable size. So, Ceres became the only dwarf planet in the asteroid belt. Eris, Pluto, and Makemake were reclassified as dwarf planets beyond Neptune. The curious orbits of the extreme trans-Neptunian objects. Out beyond Neptune, past Pluto, and far past the Kuiper belt, lies a region of the solar system that is cold, quiet, and filled with objects that move so slowly it takes centuries just to track their orbits. These are the extreme trans-Neptunian objects, or ET-NOs, and they have a strange story to tell. The first big clue came in 2012, when astronomers Chad Trujillo and Scott Shepard found a small icy body now known as 2012 VP 113. At its closest point, it still stayed far beyond Neptune. At its farthest, it swung out to over 400 astronomical units from the Sun, more than 13 times Pluto's average distance. When they looked closer, Trujillo and Shepard noticed something odd. 2012 VP 113 had its closest point to the Sun, its perihelion, in roughly the same direction as several other distant objects. These weren't planets, but small, icy bodies, members of a growing group of ET-NOs that didn't seem to be following the same rules as the rest of the solar system. Instead of having orbits pointing in all directions, these distant objects had clustered perihelia. In simple terms, they all seemed to swing in toward the Sun from a similar angle. With nothing out there to guide them, their orbits should have been spread out evenly over time, due to gravitational tugs from the giant planets. But that's not what was happening. One by one, other ET-NOs joined the list. Sedna, 2010 GB 174, 2014 SR 349, and others with long names and even longer orbits. Many of these objects shared a key feature. They had semi-major axes, the average distance from the Sun, well beyond 150 astronomical units. Some went out past 1000 AU. Their orbits were stretched like rubber bands, not circles but long ovals. The discovery of Sedna back in 2003 had hinted that something unusual was happening. Sedna's orbit never brought it closer than 76 AU to the Sun, and took it more than 900 AU at its farthest point. There was no obvious reason for such a path. It was too far from Neptune to have been flung outward by its gravity, and too close to be completely untouched by the rest of the solar system. Sedna sat in an in-between zone, one that raised questions about what or who had sculpted its orbit. Then came 2012 VP 113, and with it the realization that Sedna might not be alone. Some called this region the inner Oort cloud. Others referred to it as the Sednoids. But whatever the name, it was clear something had gathered a group of small bodies in a way that made no sense under the current models. This kind of clustering suggested a hidden influence, something big enough and far enough out to shape orbits without revealing itself directly. When Trujillo and Shepard published their findings, they suggested that a large, unseen planet might be to blame. It was only a suggestion at first, but it echoed the same kind of thinking that had once led to the discovery of Neptune when Uranus's orbit didn't behave as expected. The evidence wasn't proof, but it raised eyebrows. To make the picture clearer, more etnos would have to be found, and that wasn't easy. These objects are so far away and so small that spotting them is like trying to find a grain of sand in the middle of the ocean. They reflect very little sunlight. They move slowly across the sky. Their orbits take thousands of years to complete, so astronomers can only catch a small piece of their path at any one time. Still, surveys pressed on. With powerful telescopes scanning deep space, a few more etnos were added to the list. Each new one seemed to follow the same strange pattern. Not only did they have similar perihelia, but their orbits also seemed to tilt in similar directions. They weren't just clustered in one way, they were clustered in two. That made random chance even less likely. In a normal solar system model, with 8 planets and lots of small objects orbiting at random, these alignments shouldn't last. Over time, gravitational nudges from the giant planets, especially Neptune, should scatter the ETNOs, changing their angles and directions. But instead, the group held its shape. Some researchers began to question whether this was just a coincidence. Others wondered if it could be a trick of small numbers. After all, the known ETNOs still only number a couple dozen at most. But simulations showed that the odds of this clustering happening by chance were extremely low. Something had to be shaping those orbits. Theories poured in. One idea stood out: the presence of a distant, massive planet. This would later become the groundwork for the Planet 9 hypothesis. If a planet 5 to 10 times the mass of Earth was orbiting far beyond Neptune, it could explain the clustering. Its gravity could shepherd the ETNOs into place over millions of years. Like a cosmic shepherd, it would guide these small, icy bodies into orbits that never crossed its path, but always felt its pull. But there was a problem. Searching for new ETNOs was hard enough. Finding the hidden planet causing the effect was even harder. The outer solar system is vast, and the sky is full of stars. A small, cold planet 500 AU away would be incredibly faint. If it was on the opposite side of the Sun, it might stay hidden for years. Some astronomers remained cautious. They pointed out the possibility of observational bias. Telescopes tend to scan certain parts of the sky more than others. That could make it look like the ETNOs are clustered, even if they're not. But even after accounting for those biases, the patterns seem to hold. The ETNOs remain one of the solar system's biggest mysteries. Their orbits hint at something that doesn't fit into the standard picture of the planets we know. But for now, they continue to circle in the dark, silent and distant. The 2016 revival: how Batygin and Brown reignited the search. In early 2016, Konstantin Batygin and Mike Brown published a paper that reignited interest in a long-standing question. Is there a hidden planet far beyond Neptune? Batygin and Brown ran simulations. Dozens, then hundreds. They tested how ETNOs would behave under the influence of the 4 giant gas planets alone. They found that over time the orbits lost their alignment. The clustering didn't persist. Then they introduced a hypothetical 9th planet into the system. This planet was set on a highly elliptical inclined orbit far from the Sun, something like 400 to 800 AU at aphelion. When they did this, the clustering returned. The ETNOs held their positions, moving in a kind of synchronized dance. This model matched real data better than the null hypothesis. It didn't explain every detail, but it made a strong case that something massive, something unseen, was shaping the orbits of these distant objects. The announcement caused a stir. both in the scientific community and in the public. The press quickly dubbed the object Planet 9, partly because Brown had famously been involved in the reclassification of Pluto. Now, in an ironic twist, he was leading the charge to promote a new ninth planet, one potentially much larger than Earth. What followed was a wave of renewed attention. Other astronomers began re-examining old survey data, looking for clues they might have missed. New observing campaigns were planned, targeting the regions of the sky where Planet 9 might be hiding. Theoretical studies exploded, testing how such a planet could have formed, where it might be now, and what other effects it might have had on the solar system's evolution. One of the strengths of Batygin and Brown's proposal was its predictive power. It didn't just explain existing objects, it suggested where more might be found. Their model predicted that additional ETNOs should exist with similar orbital alignments. It also forecasted a population of objects with perpendicular orbits, strange configurations that would only make sense if a massive object had tilted them out of the solar system's original plane. Sure enough, as the years went on, new discoveries began to fit the pattern. While the debate over observational bias continued, the number of unusual orbits kept growing. Some objects appeared to follow paths that curved in the way predicted by Planet 9's influence. Others orbited at right angles to the ecliptic, suggesting they had been nudged by a tilted gravitational source. No single object proved the planet's existence, but together the growing dataset added weight to the idea. The 2016 paper brought attention back to the outer solar system as a frontier of discovery. For years, planetary science had focused on close-range missions, rovers on Mars, orbiters around Jupiter and Saturn. But now attention shifted outward again. Telescope time was dedicated to deeper searches. Grant proposals focused on long-term tracking of distant objects. The Vera C. Rubin Observatory, still in development at the time, was eyed as a potential game-changer in the search. Rather than treating each strange object as an isolated case, it provided a framework. Detached objects like Sedna weren't just weird outliers, they were potential signposts. The Kuiper Cliff, the orbital tilts, the perihelion clustering, all of it could be part of a larger story shaped by a hidden planet. There was pushback, of course. Some scientists questioned the assumptions behind the simulations. Others pointed to the low number of known ETNOs. Alternative explanations were explored. Some proposed that the observed patterns could be explained by a series of smaller objects acting together, rather than one massive planet. Others considered whether a rogue star or past encounter might have sculpted the outer solar system during its early years. Still, the core idea remained compelling. It wasn't just that the ETNOs were aligned. It was that their orbits made sense in the presence of a specific, modeled gravitational force. The more data that was added, the more the simulations were refined, the better they seemed to hold up. Batygin and Brown continued their work, publishing updates and refining the estimated orbit of Planet 9. They narrowed the search zone, but the planet itself remained unseen. Yet, even without a confirmed visual, the Planet 9 hypothesis had already achieved something remarkable. It had turned a scattered puzzle of orbital oddities into a coherent picture. It had pulled distant solar system studies back into the mainstream, and it had reminded the scientific world that there are still vast regions of our own neighborhood left unexplored. Simulating the unseen, what the models predict about Planet 9. When a planet can't be seen, but its effects seem to ripple through space, scientists turn to simulations to explore what might be hiding in the dark. This is where Planet 9 lives for now, in lines of code, in equations, and in computer models that try to match what we see in the sky with what might be causing it. The simulations that followed, the 2016 announcement by Batygin and Brown, aim to answer a few central questions. If there is a hidden planet shaping the orbits of distant solar system objects, what would that planet need to look like? How massive would it have to be? How far from the Sun? What kind of orbit would it follow? And would such a planet remain stable over billions of years? These simulations didn't start from scratch. Planetary scientists already had tools for modeling the long-term behavior of solar system bodies. The idea is to take the known positions, speeds, and masses of celestial objects, and then let gravity do its work. Step by step, the simulation calculates how everything pulls on everything else, sometimes for millions or even billions of simulated years. The goal is to see if a hypothetical planet, placed in a certain orbit with a certain mass, could explain the odd patterns observed in ETNOs and related bodies. From the earliest simulation runs, one thing became clear. If there is a planet 9, it cannot be small. To cause the kind of wide-reaching gravitational effect seen in objects like Sedna and 2012 VP 113, the planet would need to be 5 to 10 times the mass of the Earth. Anything much smaller wouldn't have enough pull to explain the alignment of multiple ETNOs, while anything much larger might destabilize the system or start affecting closer-in planets like Uranus and Neptune in ways we don't observe. The simulations also showed that the orbit of this hidden planet must be highly elongated, what astronomers call eccentric. A circular orbit wouldn't allow the planet to stay far enough away from the known planets to avoid detection, while still reaching far enough to shepherd the ETNOs into their strange patterns. Most models place Planet 9's perihelion, its closest approach to the Sun, somewhere around 200 to 300 AU. That's 5 to 7 times farther out than Neptune. Its aphelion, the farthest point from the Sun, could be as distant as 800 to 1,200 AU. The orbital period, meaning how long it takes to complete one full trip around the Sun, could range from 10,000 to 20,000 years. The tilt of the orbit also turned out to be important. The simulations that best matched real observations showed a planet whose orbit is inclined, tilted, by about 15 to 25 degrees compared to the ecliptic, which is the plane in which most planets orbit. This tilt helps explain some of the unusual orientations seen in ETNOs and in other objects with oddly inclined orbits, including a few that are nearly perpendicular to the main planetary plane. In many simulations, the presence of Planet 9 gradually lifts some objects out of the ecliptic altogether, tilting their orbits into wild new angles. One of the most intriguing features that came out of the modeling was something called orbital shepherding. Over time, Planet 9's gravity appears to gently corral other objects into specific orbital ranges. For instance, some simulations show Planet 9 forcing ETNOs to gather in specific zones of space, aligning their arguments of perihelion and preventing them from precessing or slowly changing orientation the way they would without an outside influence. This shepherding effect not only creates order where there should be chaos, but it does so over vast timescales, lending stability to otherwise unstable-looking orbits. In addition to explaining the clustering of ETNOs, the simulations also predicted something surprising: a second, perpendicular population of trans-Neptunian objects. These bodies wouldn't just be scattered or distant. They would be tilted at 90 degrees to the planetary plane or even retrograde, meaning they'd orbit in the opposite direction of the planets. These predictions were especially bold because at the time, very few such objects had been found. But as observational campaigns continued, more high-inclination and retrograde objects were discovered, including a few with orbits that matched the simulations very closely. This unexpected success added credibility to the models and gave researchers a new kind of object to look for. The simulations also helped rule out alternative explanations. For example, some scientists had proposed that the odd ETNO orbits could be due to a dense disk of smaller objects in the outer solar system rather than one large planet. But when this idea was tested in simulations, it didn't hold up well. The gravitational pull of a spread-out disk couldn't reproduce the kind of coherent clustering seen in reality. Only a massive localized body could account for the full pattern of orbital behavior. Another benefit of simulations is that they allow scientists to test the stability of Planet 9 itself. After all, it's one thing to suggest a planet might be out there, but quite another to show that such a planet could remain in a stable orbit over billions of years without crashing into other planets or being ejected from the solar system. The models showed that Planet 9, in most cases, could remain stable for the entire age of the solar system, as long as its orbit was distant enough and its interactions with Neptune and Uranus remained limited. Some simulations went further, exploring how Planet 9 might have gotten into such a strange orbit in the first place. One idea is that it formed closer to the Sun and was flung outward by gravitational interactions with Jupiter or Saturn early in the solar system's history. Another possibility is that it formed much farther out, in a cold, slow-moving region of the solar nebula, and never got pulled inward at all. There's even a more speculative idea that Planet 9 was captured from another star during a close encounter in the Sun's birth cluster, a crowded nursery where many young stars formed together. All of these scenarios could be tested in simulations by plugging in different initial conditions and watching how the system evolved over time. If a particular starting point produced a stable, aligned group of ETNOs and a long-lasting Planet 9 orbit, then it became a candidate worth considering. The power of simulations is that they turn uncertainty into a structured problem. Instead of guessing blindly, scientists can define a range of possible Planet 9 characteristics and then test them against the growing database of observed objects. It's a feedback loop. New observations inform new simulations, and the results of those simulations point toward where to look next. Each step sharpens the picture, even if the planet itself remains unseen. One limitation, however, is that they depend heavily on what we've discovered so far. If the observed ETNOs are just the tip of a much larger population, or if some of them were mischaracterized, the models might be skewed. That's why astronomers are cautious. They don't claim the planet is definitely there, only that, given the current data, a planet of a certain mass and orbit is the best explanation for what we see. How a giant planet could herd distant objects like a shepherd. To understand how Planet 9 herds ETNOs, astronomers have turned to a helpful analogy: shepherd moons. In the rings of Saturn, tiny moons like Prometheus and Pandora serve as shepherds. Their gravity shapes the edges of the rings, keeping them from spreading out. As ring particles orbit Saturn, the small shepherd moons tug on them ever so slightly. Over time, these constant subtle nudges add up, keeping the ring particles confined, aligned, and stable. The particles aren't physically tied to the moons, but they respond to the gravitational whispers that keep them in check. Now, instead of Saturn, imagine the Sun. Instead of ice particles in a ring, picture scattered icy worlds orbiting far beyond Pluto. And instead of small moons, imagine a giant planet orbiting on the edge of the solar system. That's the setup for the Planet 9 hypothesis. Just like a shepherd moon, this distant planet's gravity gently shapes the orbits of the scattered objects around it. Not in the tightly packed ring of Saturn, but across vast stretches of space. But the scale is different. Planet 9 wouldn't be orbiting just a few thousand kilometers from its subjects. It could be hundreds of astronomical units away. Its gravitational influence is slow, persistent, and accumulates over time. It doesn't yank the ETNOs into place. It leans on them gradually, shaping their paths over millions of years. The key lies in repeated long-term gravitational encounters. Imagine a distant object like Sedna swinging inward toward the Sun, then back out again into the frozen dark. If its orbit happens to bring it near the orbit of the unseen giant, then something important happens. Even if Planet 9 is nowhere nearby at the time, the potential for interaction is there. These bodies might never get close enough for a true gravitational kick, but their orbits cross paths in a way that allows slow shaping, gravitational sculpting, across time. Over many orbits, a kind of synchronization begins to happen. If the ETNO's path becomes slightly misaligned, Planet 9's gravity nudges it back. It's not a magnetic pull or a fixed connection. It's more like a pattern that gets reinforced over and over, a preferred path that the ETNOs fall into, because straying from it would make them more vulnerable to destabilizing forces. The process is not unlike the way sheep follow a certain route through a field, not because they can't go elsewhere, but because the shepherd encourages them to stay close. This gravitational shepherding works best when Planet 9's orbit is highly elliptical and tilted. That allows it to influence objects at a wide range of angles and distances. Its slow, looping path means it doesn't disrupt objects by rushing past them, but instead stays in their orbital neighborhood long enough for its gravity to matter. The ET-NOs that survive this interaction are the ones whose orbits have settled into a kind of compromise, safe from direct collisions, but still under the steady influence of the distant planet. One of the clearest signs of this shepherding is the clustering of arguments of perihelion. That's a technical way of saying that these ET-NOs all come closest to the Sun at roughly the same angle, even though their orbits differ in size and shape. In a random solar system, with no outside influence, those angles should be spread out evenly instead of being clumped together. There's also the matter of orbital anti-alignment. Some of the distant objects orbit in a way that is almost exactly opposite to Planet 9's predicted orbit. This is part of the shepherding mechanism. When an ET-NO's orbit lines up in the right direction, Planet 9's gravity actually helps keep it there. But when one starts to drift too far, the gravitational pull becomes disruptive. Those objects are either flung away, destabilized, or drawn back into alignment. Over millions of years, only the orbits that play nicely with Planet 9 survive, creating the appearance of order. This shepherding can also lift orbits out of the plane of the solar system, giving rise to high-inclination objects that orbit at steep angles. These orbits are shaped over time by Planet 9's influence, much like how a river carves a canyon. At first, the path is uncertain, but over time, the gravity clears a track. This shepherding isn't an active choice by the planet. It's not a thinking entity. But the analogy works because the process is slow, methodical, and results in structure. The distant objects move not because they're pushed hard, but because they're nudged gently and often. And in the vacuum of space, where there's nothing to stop motion, even the smallest nudge matters. This kind of orbital herding has been seen in other systems too, including exoplanet systems where multiple massive planets carve out resonances and gaps in debris disks. The physics is the same, only the setting changes. Over and over, gravity reveals its power to shape. It builds order from chaos, one slow pull at a time. Could the Kuiper Cliff be more than just an edge? For decades, the Kuiper Belt has been seen as the last real edge of the solar system, a disk of icy bodies left over from the solar system's earliest days. But this band of frozen debris doesn't stretch out forever. Around 50 AU from the Sun, the number of Kuiper Belt objects suddenly drops off. Astronomers call this sharp boundary the Kuiper Cliff. Surveys looking for distant objects find plenty of small worlds up to about 45 or 50 AU, but beyond that, the number of detections plunges. There's no gentle fade, there's no slow thinning, it's abrupt. And that has always raised questions. Is this drop-off real, or is it a limitation of our telescopes? Is the Kuiper Belt truly cut short, or are we simply not seeing what's there? At first, some scientists assumed it might be a problem of visibility. Objects farther out are dimmer, harder to spot, and require more powerful equipment to detect. But over time, more sensitive surveys ruled this out. Even accounting for brightness, sky coverage, and observation time, the sharp fall in objects beyond 50 AU still stood. If the solar system formed from a swirling disk of material, and if that disk stretched beyond Neptune, why did it stop so suddenly? The inner Kuiper Belt is full of objects in neat orbits. Many are in resonance with Neptune, locked into gravitational patterns where their periods are tidy fractions of the planet's own orbit. But farther out, those resonances fade, and the population dries up. The outer belt seems unusually empty. One early idea was that Neptune itself played a role. As it migrated outward during the early solar system, Neptune may have cleared out the outer region, disrupting objects and scattering them inward or outward. but that process should leave behind a faint trail of survivors. Some bodies should remain in the outer Kuiper belt, too far for Neptune to reach easily, but not so far that they would be completely lost. Yet they're not there, or at least not in the numbers we'd expect. This is where the Planet 9 hypothesis offers an interesting possibility. If it exists, it could have influenced the structure of the Kuiper belt early in the solar system's life. Its gravitational pull could have pushed objects out of certain regions, particularly in the 50 to 100 AU range. In this view, the Kuiper Cliff is the footprint of a larger invisible force. Simulations using Planet 9's proposed parameters show that such a planet could indeed sculpt the outer solar system in this way. Objects that would have naturally settled into the region just beyond Neptune might have been destabilized, ejected, or pulled into new orbits. Some would have been flung into the distant scattered disk. Others would have been thrown inward toward the Sun, where they either crashed into planets or were absorbed into the broader family of centaurs and inner solar system bodies. The result would be a cleared-out section of the solar system. The clearing effect doesn't have to be violent. Over millions of years, even small gravitational nudges can add up. If Planet 9's orbit sweeps through or near the 50 to 100 AU region, its influence would be felt most strongly there. The objects in that zone would find their orbits slowly pulled out of alignment, increasing their eccentricities and inclinations. Eventually, they would be removed from the stable circular orbits that define the classical Kuiper belt. This kind of reshaping explains why the Kuiper belt seems to end so sharply. It also ties into another puzzle, the fact that many distant trans-Neptunian objects don't share the flat, disc-like structure we see closer in. Instead, they're scattered in a puffier, more inclined population, some on orbits that tilt dramatically above and below the solar system's plane. If Planet 9 exists, it may have puffed up the outer solar system like this, while hollowing out the region just beyond 50 AU. In the early solar system, before any major migrations or reshaping took place, the outer belt could have been more filled in. If Planet 9 was either captured or migrated into its current orbit during a later phase, its arrival could have carved out the cliff over time. That would make the cliff not a feature of the solar system's birth, but a scar left by later events. Other ideas have been explored, of course. Some researchers have suggested that interactions with passing stars might have affected the outer edge of the belt. Others believe there may have been additional planets early on that were later ejected, altering the belt's structure on their way out. But none of these scenarios quite explain the specific and sharp nature of the drop-off, especially when considered alongside the orbital patterns of the ET nose and detached objects. Planet 9 offers a unifying thread. It connects the Kuiper Cliff to the distant bodies with aligned perihelia. It helps explain why some orbits are detached and why others are stretched and clustered. If it exists, it's not just shaping the objects we can see, it's responsible for the ones that are missing. That said, the idea is still a hypothesis. Despite years of searching, it remains a ghost in the data, a theoretical presence whose gravity is inferred from its effects. Yet the Kuiper Cliff remains one of the more compelling hints. It's a large-scale structural feature, visible across wide sky surveys, hard to attribute to coincidence or bias. It's like finding a trench in a landscape and suspecting that something once dragged through it, even if the object itself is nowhere to be found. Some have pointed out that the cliff could still be the result of observational limits in a different way. Not in terms of brightness, but in terms of sky coverage. Because many deep surveys are focused near the ecliptic, they may be missing objects that were scattered into higher inclinations. If Planet 9 or another force tilted their orbits, the outer Kuiper belt might still exist, but not where we've been looking. If true, this would mean the cliff is real only from our limited point of view, and that a more complete survey would reveal a broader population of distant worlds. The Vera C. Rubin Observatory will scan huge portions of the sky with unprecedented detail and frequency, opening a new window into the outer solar system. If the Kuiper Cliff is hiding something, whether it's distant, tilted objects or the very planet that might have caused it, those observations may be the best chance of finding out. For now, though, the cliff stands, a stark, empty region where the solar system seems to pause, a gap between the well-studied world of Neptune and the strange frontier of the detached and extreme. The tilted solar system hypothesis. The planets of our solar system follow a broad, flat path around the Sun. For centuries, this near-flat alignment seemed natural, almost expected. But when astronomers take a step back and compare the Sun's own equator to this planetary plane, a small but real mismatch appears. The Sun spins on a tilted axis, about 6 degrees off from the average orbital plane of its planets. For decades, this tilt was a curiosity. But in the context of Planet 9, it might be something more. The idea begins with the basic principle of momentum. In space, momentum is more than just motion. It's a kind of memory. When the solar system formed, everything, gas, dust, rocks, spun in the same direction, in the same flattened disk. The planets formed out of that disk and inherited its motion. They all travel around the Sun in roughly the same direction and at roughly the same angle. So if the Sun and the disk started out spinning together, why isn't the Sun's spin still perfectly aligned with the orbits of its planets? The tilted solar system hypothesis suggests that Planet 9 may be slowly, over billions of years, pulling on the entire system, nudging it just enough to create the tilt we see today. Imagine the solar system as a spinning plate on a table. The planets circle the center like small weights moving in a ring. Now picture a heavy object orbiting the plate's edge, but not in the same flat circle. Its path is tilted, looping in a wide arc above and below the plate. Its gravity exerts a slow but steady torque or twisting force on the entire structure. Not enough to flip the plate, but enough to make the whole thing lean ever so slightly off-center. This is what Planet 9 could be doing. If it's orbiting the Sun at a steep angle, somewhere around 15 to 25 degrees above the average planetary plane, then its long-term gravitational influence wouldn't just pull on Ethnos. It would act on the whole inner solar system too. Over time, the combined orbits of Jupiter, Saturn, Uranus and Neptune would be coaxed into a new orientation, not in any single moment, but slowly, through repeated, gentle pressure, like the effect of ocean currents shifting a coastline over centuries. Computer models show how this would work. They start with a hypothetical Planet 9, maybe 6 Earth masses, traveling on an inclined orbit with a distant perihelion. Then, using the laws of motion and gravity, the simulation lets the system evolve over time. The orbit of Planet 9 subtly alters the entire angular momentum vector of the known planets. The solar system's midplane, the imaginary surface that cuts through all the planetary orbits, starts to shift. After 4.5 billion years, the result is a tilt of about 5 to 6 degrees. That's almost exactly what we see. Importantly, this tilt isn't the kind of thing that could come from a passing star or a one-time event. A stellar flyby, which some theories suggest may have shaped objects like Sedna, would be brief. It might distort orbits in the far outer solar system, but it wouldn't gradually torque the planetary plane. The tilted solar system hypothesis requires a persistent, ongoing influence, something that's still out there, still orbiting, and still quietly working. The gravity of Jupiter and Saturn is immense, but they are embedded in the same plane as the other planets. Their influence is part of the system's normal internal balance. What makes Planet 9 unique is not just its mass, but its distance and tilt, because it circles so far out and so off-axis. Its gravitational pull doesn't cancel out like the others. It acts from above and below, pushing at an angle. Over time, that angled force adds up. There's another twist to this story. While the planets are tilted relative to the Sun's equator, we also see that their tilt remains consistent with each other. The ecliptic, the plane of Earth's orbit, is not wobbling. It's stable. That means whatever caused the tilt must have acted on all the planets as a group. This again supports the idea of a distant perturber acting on the solar system as a whole, not just isolated regions. It also offers a rare insight into how delicate and interconnected the system really is. Something orbiting far beyond Neptune, invisible to our telescopes, might be shaping the very framework in which the inner planets move. The solar system is not a collection of isolated orbits, but a single, flexible structure, one where mass in the outskirts can affect motion near the center. In a sense, Planet 9 would be like a hidden weight at the edge of a mobile sculpture. Its presence tips the balance, even if we can't yet see the string it's pulling. The entire solar system shifts in response. If our Sun can be tipped by an outer planet, might other planetary systems show similar features? Observations of exoplanet systems have shown a wide range of alignments. Some stars have planets that orbit in very strange planes, some even backwards relative to the star's spin. While those cases likely have different causes, the principle remains. Planets can change the shape and alignment of a system over time. Back home, the more we understand the Sun's own motion, the more the picture comes into focus. The exact measurement of its spin axis, compared to the plane of the planets, is one of the many quiet puzzles that had no clear cause. Planet 9 might not only explain strange orbits far away, it might explain the lean of the whole planetary disk. It's not proof, but it's another layer of evidence, another connection between the seen and the unseen. The tilted solar system could be the legacy of a giant that still waits in the dark. Could a planet-like swarm of small objects mimic a giant's pull? Instead of one large, unseen planet shaping the outer solar system, what if the cause is many smaller bodies, spread out, faint, and moving in the deep dark far from the Sun? This kind of mass arrangement is called a distributed mass scenario. It means the gravitational influence isn't coming from one place, but from many. Picture not a shepherd dog guiding a flock, but rather a hilly landscape slowly shifting the paths of wandering animals. Over long timescales, even small forces can have major effects. The idea is that a broad population of objects, each one too small to cause much of a stir alone, might still add up to something significant. In some ways, this suggestion makes sense. The outer solar system likely contains far more objects than we've discovered. We already know about the Kuiper belt. Beyond that lies the scattered disk, and even farther, the realm of detached objects like Sedna and 2012 VP 113. These distant zones are barely mapped, but they're expected to contain many icy remnants from the early solar system. If enough mid-sized bodies, perhaps hundreds or thousands of them, exist in these distant regions, their combined gravity could act like that of a single larger mass. This could, in theory, account for the clustering and orbital tilt seen in Etienne's. But there are challenges with this idea. For one, the mass required is not small. To recreate the kinds of perturbations seen in the simulations for Planet 9, the total mass would need to be several times that of Earth. Right now, the known mass of the Kuiper belt and scattered disk combined is much smaller, probably only a fraction of an Earth mass. This means that if a distributed mass model is correct, we've either vastly underestimated the number of objects out there, or we've misunderstood how mass is arranged in those distant regions. Some researchers argue that a swarm of large yet still undiscovered objects could be hiding in the dark. These wouldn't be Earth-sized, but perhaps each the size of the Moon or Mars. If dozens or hundreds of them existed far beyond Pluto, they could help shape the orbits we see today. But such a swarm raises more questions. Why haven't we seen even a few of these mid-sized objects already? While it's true that distant bodies are hard to detect, something the size of Mars would still reflect some sunlight. If one passed near the inner edge of its orbit, say 60 to 70 AU from the Sun, our telescopes might pick it up. Yet no such discoveries have been confirmed. Most of the distant objects we've found are small, tens to hundreds of kilometers wide, not planetary in scale. Another issue is how such a swarm would behave over time. Simulations of multiple object distributions show that it's harder to keep orbits in long-term alignment, while a single massive planet can exert a steady, predictable influence. A swarm made of many bodies might act more chaotically. Each piece would have its own orbit, and their gravitational pulls would overlap and interfere. Over millions of years, these interactions could break the neat patterns seen in the orbits of the etnos. Instead of keeping objects clustered, the mass might cause them to spread out. Still, some researchers believe there could be a middle ground. What if the swarm isn't evenly spread, but instead concentrated in one part of the sky? If the distribution is lopsided, more like a blob or arc than a full ring, it might create the illusion of a single source of gravity. In this case, the mass wouldn't be centered at a point like a planet, but its overall effect could mimic a planet's pull. This concept is hard to test, though. It depends on where the objects are, how they move, and how well our surveys can detect them. How would such a massive swarm have come to exist in the first place? Planetary formation models suggest that most of the solar system's solid material ended up in the inner regions, where it formed the terrestrial planets, or in the region of the gas giants. The outer solar system was less dense and slower to evolve. For a large population of mid-sized objects to form beyond 100 AU, conditions would have to be different than current models suggest. Maybe some unusual event, like disk instability, created a pocket of dense material far from the Sun, which then formed into many objects. But such a scenario would be rare and would need strong evidence to be convincing. Observational data might one day provide that evidence. The next generation of sky surveys will scan wide areas of the sky in great detail. They may detect new distant objects, map their orbits, and refine estimates of how many bodies are out there. If a pattern emerges showing many undiscovered mid-sized objects, the distributed mass idea could gain support. But if those objects fail to appear, or if their arrangement doesn't support the needed gravitational influence, the idea will lose ground. There's also a hybrid possibility to consider. Perhaps both ideas are true to some extent. Maybe Planet 9 does exist, exerting the main influence on the outer solar system, but a background population of other bodies adds smaller perturbations. In this picture, the distant solar system is shaped by layers of influence, one dominant player and many minor ones. That wouldn't be unusual. Even in the inner solar system, small effects matter. The Yarkovsky effect, a tiny push caused by the way asteroids absorb and re-emit heat, can slowly change their orbits over time. If such subtleties matter at close range, the cumulative pull of many small objects might matter at great distances. The swarm hypothesis is a valuable part of the conversation because it keeps the focus on possibilities beyond the simplest answers. Science thrives on alternative models. By comparing how different ideas match up with observations, researchers get closer to the truth. Even if the swarm model turns out to be wrong, testing it helps sharpen the case for or against Planet 9. Testing the Nemesis hypothesis, Planet 9's dark twin. In the 1980s, some scientists noticed that mass extinctions on Earth seem to occur in a regular cycle, roughly every 26 million years. Could something out there be disturbing the outer solar system on a schedule, sending comets inward and triggering global catastrophes? From this question came the Nemesis hypothesis, the idea that the Sun might have a companion star, a small faint object that orbits far beyond Pluto, perhaps circling the solar system every tens of millions of years. If real, Nemesis wouldn't be a bright companion like a twin sun in the sky. It would be something much dimmer, a red dwarf star, or perhaps even a brown dwarf giving off little or no light of its own. Its orbit would take it far into interstellar space, returning only after long stretches of time to disturb the Oort cloud, the huge shell of icy bodies that surrounds the solar system at a distance of thousands of AU. The Nemesis idea was bold and imaginative, but it was always on uncertain ground. It was hard to prove and harder to observe. Early infrared sky surveys failed to find any sign of a nearby dim star, even one as faint as a brown dwarf. With time, enthusiasm faded, and the idea of Nemesis was largely set aside. But it never quite vanished. In recent years, with the renewed focus on Planet 9 and the strange behavior of etnos, the Nemesis idea has crept back into the discussion, not as a cause of extinction, but as a possible explanation for the outer solar system's orbital oddities. Could a more massive object, something heavier than a planet, but smaller than a full star, be lurking in the dark, shaping orbits from afar? Unlike Planet 9, Nemesis was imagined as far more massive, up to 1/10 of the Sun's mass, or more. That kind of mass would exert enormous gravitational influence. It could easily disturb the orbits of comets and outer solar system objects, and perhaps explain the mysterious patterns we see today. But there's a problem. The larger the mass, the easier it should be to detect. And so far, we haven't. Several sky surveys have looked for brown dwarfs and other faint objects in the nearby galaxy. The Wide Field Infrared Survey Explorer, or WISE, a NASA mission launched in 2009, was particularly well suited to the task. WISE scanned the entire sky in infrared light, which is ideal for spotting cool, dim objects like brown dwarfs. If a Nemesis-like body were within about 1 light-year of the Sun, WISE likely would have seen it. But it didn't. That finding put tight constraints on the Nemesis idea. It suggested that no brown dwarf larger than about 10 Jupiter masses is hiding within our solar system's neighborhood, but that doesn't fully close the door. There's still room, in theory, for something smaller. A super-Jupiter object that's cold, faint, and far enough away to have escaped notice. It would be larger than Planet 9, but not as big as the Nemesis originally imagined. Somewhere in between lies the grey area where some theorists now explore possibilities. This middle ground version of Nemesis, less a killer star and more a massive rogue, could still affect the distant solar system. It might reside in an extremely wide elliptical orbit, taking it thousands of AU from the Sun at its farthest point. In such a position, it could gradually nudge the orbits of objects in the scattered disk or even the Oort cloud. Over time, these small effects could build up, tilting or clustering orbits in ways we now associate with Planet 9. One idea is that if such a body existed early in solar system history, it might have helped sculpt the structure we see today, even if it's now gone or no longer active. Maybe Nemesis wasn't a permanent companion, but a captured object, a rogue planet or brown dwarf that passed through the Sun's gravitational field, disrupted things for a while, and then moved on. Or maybe it's still out there, in a long orbit that keeps it hidden most of the time. Some astronomers have pointed out that the Sun may have formed in a dense stellar nursery, surrounded by other stars packed closely together. In such an environment, the chances of capturing a wandering object would be higher. Maybe during the early years of the solar system, the Sun grabbed a passing brown dwarf, which then fell into a long, looping orbit around it. Or maybe a close stellar encounter nudged the outer solar system and kicked some objects into detached orbits like Sedna's. The idea of an early capture event is appealing because it could explain some of the strange features we see without requiring a massive permanent companion. It also fits better with the limits imposed by surveys like WISE. If Nemesis were only briefly gravitationally bound to the Sun, it might have already escaped. Its fingerprints would remain, but the object itself would be gone. Still, as interesting as these ideas are, the lack of observational evidence weighs heavily. A brown dwarf with even a small fraction of the Sun's mass should glow faintly in infrared. If it's nearby enough to affect distant solar system objects, it should appear in sky maps. But aside from a few ambiguous blips and candidate detections that didn't pan out, nothing has been confirmed. Yet science doesn't throw away ideas just because they're hard to test. It sets boundaries and keeps checking them. As technology improves and new instruments begin scanning the sky with unprecedented sensitivity, the window may close further or swing open in a surprising direction. If something Nemesis-like is eventually found, it would have enormous implications. It would change our understanding of the solar system and raise questions about how common such companions are. Maybe our Sun isn't alone in once having a dark twin. Maybe binary or multiple systems are the rule, and lone stars like ours are the exception. For now, the Nemesis hypothesis remains on the fringe, part history, part mystery, part challenge to modern astronomy. Its shape has changed over time, from a death-dealing star to a quiet massive perturber. But the core idea remains part of the broader search for what lies beyond. Whether it turns out to be a brown dwarf, a super Jupiter, or nothing at all, the questions Nemesis raised continue to echo in the work of scientists pushing the boundaries of our knowledge about the solar system. Modified gravity versus Planet 9, competing explanations. When astronomers face strange movements in the solar system that don't seem to follow the usual rules, one path they often take is to search for hidden objects. But there's another way to look at the problem. Instead of asking if something out there is pulling on objects in an unexpected way, some scientists ask whether our understanding of gravity itself might be incomplete. This line of thinking doesn't point to a planet. It points to a possible flaw, or at least a limit, in the laws of gravity as we currently know them. These ideas fall under what's called modified gravity theories. They suggest that under certain conditions, especially when things are very far apart or moving very slowly, gravity might not behave the way Newton or Einstein said it should. The most well-known of these is MOND, short for Modified Newtonian Dynamics. MOND was first proposed in the 1980s, not to explain strange orbits in the solar system, but to deal with another mystery entirely: why galaxies seem to spin faster than they should. According to Newton's laws, the stars in the outer parts of galaxies should move more slowly than stars near the center, because there's less mass pulling on them. But they don't. They move as if there's extra mass hidden somewhere, invisible mass or dark matter. Instead of assuming all this missing mass really exists, MOND tries something else. It suggests that when gravity gets very weak, like in the outer reaches of galaxies, it acts differently than Newton said. It becomes stronger than expected, without needing extra mass. This would help explain why stars in galaxies don't slow down as they should. The force of gravity just behaves differently at that scale. Most of the focus on MOND and similar theories has stayed in the realm of galaxies and the large-scale structure of the universe. But some researchers have wondered if these same changes might also have subtle effects in our own solar system, especially in its farthest parts, where gravity is weakest. If ETNOs are acting strangely, maybe it's not because something is pulling on them from a great distance, but because the rules we're using to describe their motion are slightly off. One version of this idea involves what's known as the external field effect. In MOND, gravity inside a system like the solar system doesn't just depend on the masses involved. It can also depend on the gravitational pull from the galaxy as a whole. That's very different from Newtonian gravity, where distant gravitational forces tend to cancel out and don't play much of a role in a system's local behavior. The idea here is that the solar system doesn't exist in isolation. It's part of the Milky Way, and the Milky Way's own gravity might change how weak forces act inside the solar system. That could explain why some objects beyond Neptune behave in odd ways, clustering or tilting when they shouldn't. It's not because of a hidden planet, it's because gravity in this weak force zone acts differently. This kind of explanation is subtle. It doesn't show up in the inner planets, where gravity is strong and behaves just like Newton predicted. But farther out, way past Neptune, in the domain of objects like 2012 VP 113, the forces are so gentle and the orbits so long that even a tiny change in how gravity works could make a big difference. Some simulations have tried to test these ideas. By applying modified gravity formulas instead of the usual Newtonian ones, researchers look to see whether the same strange clustering and orbital alignment seen in ETNOs can arise naturally. In some cases, the results look promising. A few simulations show that MOND-like laws can cause distant objects to behave much like they do in the real solar system, without needing a Planet 9 to explain them. But this approach has problems too. One issue is that MOND, while it works well for galaxies, has a harder time fitting all the details of the solar system. Gravity has been tested with incredible precision using spacecraft data, planetary orbits, and radio signals. And so far, within the realm of known planets, Newtonian physics continues to hold up. Any new version of gravity has to match all those successful predictions while also explaining what's going on farther out. Another issue is that MOND doesn't have a full theory behind it. It's more of a mathematical rule than a physical explanation. Over the years, people have tried to build full theories of modified gravity that include relativity and fit with what we know about the rest of the universe. Some of these are known as TVs, or other more complex frameworks, which aim to give MOND a foundation in the kind of field equations Einstein used. But these theories tend to be more difficult to apply to the solar system without running into conflicts with existing data. Still, the appeal of these ideas is strong. If gravity changes in some small way under certain conditions, that might explain more than just the strange behavior of ETNOs. It might also help with larger puzzles, like dark matter and cosmic structure. That kind of elegance is what many physicists find attractive. On the other hand, the Planet 9 idea is simple in a different way. It doesn't require rewriting the laws of nature. It just asks whether there's something out there we haven't seen yet. And in some ways, that's more comfortable. We've added new planets before when orbits didn't make sense. That historical precedent gives the Planet 9 hypothesis a kind of built-in credibility. It's a familiar method. Observe strange motion. Propose a new object. Look for it. If we find it, the mystery is solved. If not, the theory adjusts or gives way. But modified gravity theories don't offer something to look for. They change the way we interpret what's already there. That makes them harder to test directly and also harder to disprove. If someone suggests that gravity is a little different out past 100 AU, it's tough to check that unless you can send a probe there or detect effects that don't fit anything else. This tension between discovering new objects and adjusting old laws is one of the core debates in modern astronomy. It plays out not just in the outer solar system, but across the universe. Whenever we see motion we don't understand, we have to ask, is something pulling that we can't see? Or is gravity itself playing tricks? If a planet is found, it would explain a lot. But if it isn't, if the evidence continues to mount, but no planet ever shows up, then the attention may shift even more toward theories like MOND. In that case, the solar system may turn out to be a testing ground, not just for hidden planets, but for the very nature of the universe's most familiar force. Could a primordial black hole be hiding in the Kuiper belt? In recent years, another idea has started to get attention. One that sounds far more exotic, yet fits neatly into the world of gravitational influence. What if the mysterious force isn't a planet at all? What if it's something darker, older, and almost impossible to see? What if it's a black hole? Not the kind of black hole found in the centers of galaxies or born from dying stars, but a smaller, ancient one, possibly no larger than a grapefruit, yet as massive as Earth. It would be what physicists call a primordial black hole, and if it exists, it could be hiding in plain sight at the edge of our solar system. Primordial black holes are a theoretical type of black hole that might have formed in the early universe, long before stars and galaxies. Right after the Big Bang, the cosmos was hot and dense, with regions that could have collapsed under their own gravity, forming tiny black holes. Unlike the ones made when stars explode, these wouldn't come from dead stars at all. They would be relics of the universe's first moments. Most would have evaporated quickly through a process known as Hawking radiation, but some could have lasted, especially those with masses similar to planets. A black hole with the mass of Earth would be incredibly compact, just a few centimeters across. It would be entirely invisible in reflected sunlight, but its gravity would work just like any other object of the same mass. If there is a massive, unseen object affecting the orbits of ETNOs, then maybe that object doesn't have to be a planet. Maybe it's a black hole, ancient and cold, drifting quietly through the Kuiper belt or beyond. The idea was brought into the spotlight by a group of researchers in 2019 who suggested that a primordial black hole could account for the same effects attributed to Planet 9. The strange clustering of orbits, the aligned angles, the tilt of the solar system, all could be caused by a small black hole if it was in the right place. Since a black hole of Earth mass exerts gravity just like a planet of the same mass, the orbital effects would be nearly identical. The main challenge is detection. A planet, even a faint one, could reflect sunlight or give off infrared radiation. A black hole, on the other hand, emits no light. It absorbs everything. Even space telescopes designed to pick up heat would likely miss something so small and so cold. That makes direct observation very unlikely. But scientists have looked for other clues. One way to find a black hole in the outer solar system is to catch it interacting with other things. For example, if a black hole passed near a small body like an asteroid or comet, its gravity could cause a lensing effect, bending and magnifying the light of background stars. This is known as gravitational microlensing. It's rare and hard to spot, but surveys like the optical gravitational lensing experiment have found events like these in other parts of the sky. If a primordial black hole were orbiting in our solar system, it might occasionally cause a microlensing event that could be detected from Earth. Some researchers have proposed dedicated missions to search for these flashes. Others have suggested looking for signs of disruption among small objects in the Kuiper belt, sudden changes in their orbits that might hint at a passing, invisible mass. Another line of thinking involves dark matter. Some versions of the primordial black hole theory propose that these black holes might actually make up a portion of the dark matter in the universe. If that were true, and if dark matter tends to cluster around galaxies, then finding one in our own solar system wouldn't be out of the question. It would just be incredibly rare. But rarity doesn't mean impossibility. If even one primordial black hole is out there, it could help explain not just the odd movements of distant solar system objects, but also offer a glimpse into the nature of dark matter and the conditions of the early universe. It would be a discovery with implications far beyond planetary science. Because the object would be so hard to find, the evidence would remain indirect. If we do detect orbit disturbances or unexplained lensing events, they could just as easily be caused by a hard-to-see planet rather than a black hole. Also, without radiation or other emissions, tracking a black hole's exact position would be nearly impossible until we had better observational tools. Still, some scientists consider this idea a serious candidate. It combines known physics, black holes, gravity, orbital dynamics, with a natural extension of cosmic history. There's no need to invent new laws of gravity. A primordial black hole is odd, but not impossible. Black holes are usually thought of as cosmic monsters, huge, distant, feeding on gas and stars. But this idea paints a quieter picture. A black hole no bigger than an orange, cold and ancient, drifting slowly among frozen worlds, pulling gently on the outer edge of our solar system. If a primordial black hole is out there, it may take decades to find it, or it might remain hidden forever. Even so, just thinking about the possibility has pushed astronomers to ask deeper questions about how we understand gravity, mass, and the unseen parts of our own backyard in space. Exploring the hypothesis of Planet 9 as a captured rogue planet. What if Planet 9 didn't form here at all? This is the captured rogue planet hypothesis, and it starts with the idea that our solar system may not be a closed system. In the early days of the universe, stars were not born alone. They formed in crowded nurseries, with dozens or even hundreds of siblings packed closely together in the same region. These young stars orbited the center of their birth cluster, jostling for space, each surrounded by its own developing disk of gas and dust. It was in these disks that planets formed. But in such a chaotic environment, not every planet stayed close to its star. Some were flung out during violent interactions with other planets or stars. These ejected worlds became what are known as rogue planets, planets without a star. Adrift in the dark, they moved silently through interstellar space, no longer bound to any one system. Surveys have found evidence that the Milky Way could be filled with them. Some estimates say there could be billions, maybe even more. The idea that the Sun could have captured one of these wandering planets might seem unlikely, but under the right conditions, it's possible. If a rogue planet passed close enough to the Sun early in its history, especially during the time when the Sun still had a surrounding cluster of stars. The gravitational tug of the Sun could have slowed the rogue down and trapped it. This would only work if the encounter was just right. If the planet came in too fast, it would fly past. If it came too close, it might be pulled in too quickly and slingshotted out again. But a slow, wide approach in the crowded conditions of a star-forming region might lead to a successful capture. This would explain some of the odd traits expected of Planet 9. For one, its orbit would be highly elliptical. It would take thousands of years to complete a single trip around the Sun. It might also be inclined compared to the rest of the solar system. These are all signs you might expect from an object that wasn't born in the same disk of gas and dust as the other planets. A captured planet might be an outsider, holding on loosely, orbiting on a strange long path. This would explain why it hasn't been seen yet, because it spends most of its time far from the Sun, in the darkest reaches of the system. When it's at its farthest point, or aphelion, it would be faint, cold, and moving slowly. Detecting such a world with current telescopes is difficult, especially if astronomers don't know where to look. Simulations have shown that capture events like this are rare, but not impossible. In 2017, a study modeled how the Sun, in its early life within a star cluster, could have trapped a passing planet. The researchers found that the Sun would have had the best chance of capturing such an object in the first 100 million years of its life, when the solar system was still forming and the surrounding cluster was still dense. If this happened, the captured planet could now be orbiting in the distant reaches where Planet 9 is suspected to lurk. If Planet 9 is a captured rogue, it means that our planetary family includes an adopted member. It suggests that planets can move not just within their own systems, but between them. And it raises new questions about what else the solar system may have encountered in its long life. A captured rogue planet should differ in composition from planets that formed here. It could have a different mix of elements or a different internal structure. Maybe it has moons of its own, pulled in during its travels. Maybe it's surrounded by a ring system or covered in clouds unlike any we've seen before. Since it would have formed around another star, the conditions could have been very different, hotter, cooler, or more turbulent. If we ever locate Planet 9 and study its makeup, we might be able to tell whether it formed here or came from somewhere else. Differences in chemical signatures could offer clues. For instance, the ratio of hydrogen to helium in its atmosphere, or the types of ices found on its surface, might not match what we see on Neptune or Uranus. These subtle differences would help confirm whether it's a local planet or a traveler from another system. Of course, other theories still compete for attention. Some suggest Planet 9 formed in our solar system and was later pushed out to a distant orbit. Others question whether any single object is needed at all. But the captured rogue idea stands out because it fits with what astronomers are learning about the galaxy. The idea that stars can trade planets, passing them from one to another during their early lives, challenges older views of solar systems as isolated and static. Instead, it paints a picture of a busy, dynamic universe. Rogue planets are becoming a focus of study. The more we learn about these lonely worlds, the better we'll understand how common they are, and how one of them might have ended up in our own backyard. Why Planet 9 has eluded our best telescopes. Despite years of effort and some of the most powerful telescopes on Earth and in orbit, Planet 9 remains hidden. This isn't just a matter of bad luck. There are specific reasons why spotting it is so difficult. Each one on its own would be a challenge. Together, they've made finding this object one of the most elusive goals in modern astronomy. The first and most basic problem is brightness. Any object that far from the Sun is incredibly faint. Planet 9 wouldn't be glowing on its own. It would shine only by reflecting sunlight. And at such vast distances, sunlight gets very weak. The intensity of light drops with the square of the distance. That means even a big reflective planet gets dim fast as it moves away from the Sun. If Planet 9 is, say, 600 AU out, it's getting just 1/360,000th the sunlight that Earth receives. The light that does make it to the planet and bounces back to us still has to travel all the way to Earth. Again, the brightness of that returning light fades with the square of the distance. So not only is the planet getting very little sunlight to begin with, the small amount of reflected light also has to make a very long journey through space. All that means even the most sensitive telescopes are working near their limits just to detect its faint glow. Surface composition plays a big role too. Not all planets reflect light the same way. Some are dark and dull, others are bright and icy. Astronomers use the term albedo to describe how reflective a surface is. An object with an albedo of 1 reflects all the light it receives, like a perfect mirror. An albedo of 0 means it reflects nothing, like a black hole. Icy objects like Pluto or some of the large moons of the outer planets can have albedos around 0.6 to 0.9. But darker rocky objects like many asteroids or comets can have albedos as low as 0.04 or 0.05. That's just 4% or 5% of the sunlight being bounced back. So, if Planet 9 has a dark surface, if it's covered in soot-like material, space-weathered ice, or organic-rich compounds, it could reflect only a tiny fraction of the sunlight it gets. It's not just dimness that causes trouble, it's motion too. Objects in the far solar system move slowly. At 600 AU, a planet would take about 15,000 years to complete one orbit. So over days or even weeks, it would barely shift position in the sky. That's a problem because astronomers often rely on movement to find new solar system objects. Telescopes take multiple images of the same region hours or days apart, looking for dots of light that change position. That's how Pluto was found. It was spotted moving between stars, but a planet as distant as Planet 9 would move so slowly that it could be mistaken for just another fixed star. Even if astronomers know where to look, spotting such a slow, faint object would require taking long exposure images and coming back to the same spot again and again over months. Most telescope surveys are not set up to do that. Time on big telescopes is precious and often scheduled for other kinds of science. And with such a huge area of sky to search, the chances of happening upon the right spot without guidance are slim. That leads to the next major problem. We don't know exactly where Planet 9 should be. Based on computer simulations, astronomers can make guesses about the most likely areas, but these are still broad swaths of the sky. The region where Planet 9 might be is large, tens of thousands of square degrees. Even with high-tech cameras, covering that much sky is a huge task. The problem gets worse when you consider that Planet 9 could be near the Milky Way's band in the sky. This region, filled with dense clusters of stars, dust, and gas, is notoriously hard to search. It's like trying to find a dim light bulb against the background of a glowing city. If Planet 9 happens to lie against that backdrop, its faint light could easily be drowned out or confused with a field of similar-looking stars. Compounding the challenge is the shape of Planet 9's orbit. Many models suggest a highly stretched-out ellipse. If it's currently near the farthest point in its orbit, then it's at its faintest and hardest to detect. This wouldn't be unusual. Even Neptune, when it was discovered, was found partly because it was near perihelion, closer to the Sun, and therefore brighter and easier to observe. If Planet 9 is on the opposite end of that spectrum, it might still be out of reach for now. While modern telescopes like the Subaru telescope in Hawaii and the Dark Energy Survey in Chile have searched some of the sky for Planet 9, their capabilities, while powerful, still face limits when it comes to slow-moving, faint objects. Many existing surveys are optimized for other goals, like tracking near-Earth asteroids, mapping galaxies, or looking at cosmic microwave background radiation. None of these are tuned specifically for finding a large, dim object on the very edge of our own solar system. The upcoming Vera C. Rubin Observatory will conduct a 10-year survey of the southern sky called the Legacy Survey of Space and Time, or LSST. This telescope will take images of the entire southern sky every few nights, looking for changes over time. Its large mirror and wide field of view make it one of the best hopes for detecting Planet 9. Still, even with Rubin, it could take years of scanning and cross-checking data before something shows up. A single night of observing with Rubin will generate terabytes of data. Sorting through all of that to look for a dot that shifts slightly over weeks or months is a massive task. It's a needle in a haystack problem, not just in the sky, but in the data. That means astronomers must rely more and more on machine learning and pattern recognition tools, using algorithms to flag possible objects that show the right signs of motion, brightness, and orbit. Even then, follow-up observations with other telescopes are needed to confirm what's been found. It's a slow, careful process. It's worth remembering that Pluto, even though much closer and brighter than Planet 9 would be, was itself nearly missed. It was found through a long, patient search that relied on photographic plates and visual comparison. Today, with so much more sky to examine and so many more stars in view, the chance of missing an even fainter object is far higher. So far, all efforts to spot Planet 9 directly have come up empty. This challenge highlights something important about astronomy. Even with advanced technology and years of theoretical work, nature can still hide things from us. Bright stars and nearby planets may be easy to find, but the solar system is wide and deep. Faint objects, especially those moving slowly and in unexpected directions, remain hard to spot. Infrared searches and the limits of WISE and LSST. Launched in 2009, WISE was designed to scan the sky in the mid-infrared, a range of wavelengths that can detect objects too cool or dim to appear in regular telescopes. Originally, its mission was to catalogue asteroids, brown dwarfs, and dusty galaxies. But after it finished its primary mission, astronomers realized it had gathered data that might be helpful for looking for large, cold objects in the outer solar system. WISE carried detectors that were sensitive to 4 infrared bands, 3.4, 4.6, 12, and 22 microns. These wavelengths are especially good at catching the faint heat from objects in space that don't reflect much sunlight, but are still warmer than the deep space background. That includes brown dwarfs, gas giants, and potentially even Planet 9. The idea is simple. If Planet 9 should still retain some internal heat, that heat would leak out slowly over billions of years, making the planet just warm enough to glow faintly in the infrared. Not bright, certainly nothing like a star, but enough to leave a signature. And since space is so cold, just a few degrees above absolute zero, even a weak infrared source can be noticeable if you know what to look for. Researchers dove into WISE data, scouring the full sky maps for signs of such an object. They filtered out known stars, galaxies, and nearer solar system bodies. They looked for anything moving slowly across the sky with the right temperature and brightness profile. For a while, there was hope that WISE might actually reveal something. But so far the results have been negative. No candidate for Planet 9 turned up in its data. That doesn't mean Planet 9 isn't out there. But it does tell us something about what it can't be. Based on WISE's sensitivity, astronomers have been able to place limits on the possible combinations of size, distance, and temperature that Planet 9 could have. For instance, a Jupiter-sized planet within 25,000 AU would likely have been detected. A Saturn-sized object would be visible out to perhaps 10,000 AU. But a smaller, colder planet located around 600 to 1,000 AU would be dimmer in the infrared, possibly slipping below WISE's detection threshold. WISE, like most space telescopes, had limitations. Its detectors were sensitive, but they couldn't see everything. The telescope's scan strategy meant that some parts of the sky were covered better than others. And after its cryogenic coolant ran out, WISE could only observe in its 2 shortest wavelength bands, 3.4 and 4.6 microns, which limited its ability to detect the coldest, faintest objects. Later, WISE was reactivated under the name NEOWISE, with a focus on near-Earth asteroid detection, but it no longer had the full infrared capability it once had. This is where other efforts might help. While Rubin and LSST will work primarily in visible and near-infrared light, not the mid-infrared like WISE, it has another major strength. it will return to the same parts of the sky again and again over the course of years. Still, LSST won't be able to match WISE when it comes to detecting faint heat. That's not what Rubin was designed for. So the Rubin Observatory can help us find Planet 9 if it reflects enough sunlight, but it won't be as helpful in picking up thermal emissions. To fill in that gap, astronomers look toward future infrared missions. One candidate is the James Webb Space Telescope, or JWST, which has some capacity in the mid-infrared and much greater sensitivity than WISE. But JWST isn't a survey telescope. It doesn't scan the whole sky, it targets specific regions. That makes it useful for follow-up, but not ideal for the initial hunt. Another hopeful future mission is the proposed Nancy Grace Roman Space Telescope, which will also offer wide-field infrared imaging, though again, not in the same thermal bands as WISE. The truth is, there's no current or planned mission that completely replaces WISE's original infrared all-sky capabilities at its full range. This leaves us with a hole in our search strategy. If Planet 9 is warm enough and close enough to be visible in infrared, but too cold or distant to be seen in optical bands, we might need a new dedicated mission to find it. In the meantime, the limits set by WISE are important. They help rule out certain scenarios. For example, Planet 9 can't be too massive or too warm, or we would have seen it already. It also can't be too close, or again, it would have shown up in the data. What's left is a narrow but still possible range of properties. A mid-sized planet, colder than Neptune, somewhere in the range of 400 to 1000 AU. It would be invisible in most optical telescopes and just below the detection limit in the infrared. This middle ground is a frustrating place for astronomers. It's a blind spot, a zone where our current tools, both optical and infrared, are near their limits. Every time a new survey comes online or a telescope pushes its capabilities, scientists hope that maybe, finally, Planet 9 will be dragged out of hiding. But until then, it remains a shadow, neither ruled out nor confirmed, hiding in the gap between what we can see and what we can't. The southern sky blind spot. Are we just looking in the wrong place? The sky is vast, and covering all of it equally is nearly impossible. Over the decades, most of the deep sky surveys have been biased, geographically, toward the northern hemisphere. This isn't because of some scientific preference, but rather a matter of practicality. The world's largest and most productive observatories have traditionally been built in the northern half of the globe. From those locations, much of the northern celestial hemisphere is easily accessible year-round, while large chunks of the southern sky either skim the horizon or stay out of view entirely. This has created what some astronomers refer to as a southern sky blind spot. It's not total darkness. There are excellent southern observatories, such as those in Chile and Australia. But in terms of cumulative survey time, depth, and repetition, the southern sky has received far less attention overall. Many of the surveys responsible for finding trans-Neptunian objects and tracking distant Kuiper belt bodies have concentrated heavily on regions of sky visible from mid-northern latitudes. It's understandable from a logistical perspective, but it leaves open a big question. Could Planet 9 be lurking in that lesser-searched half of the sky? If so, it might explain more than just its apparent invisibility. Many simulations of Planet 9's orbit suggest it could spend a large part of its journey through space below the plane of the solar system. And depending on where it is in its hypothetical orbit today, it might be situated deep in the southern celestial hemisphere, somewhere between the southern constellations. These regions are only visible to a smaller number of facilities, often for shorter portions of the year, and sometimes with less survey support or weather consistency. That alone would make detection harder, even for a relatively large and influential body. Even when southern sky surveys do operate, they may be focused on different goals. For instance, some of the telescopes in Chile, located in prime observing locations, are used primarily for extragalactic astronomy. Their cameras and instruments are tuned for deep, narrow looks at distant galaxies and cosmic background signals. Others may be focused on different parts of the sky, like the center of the Milky Way. They may not repeat observations with the kind of frequency needed to track slow, dim solar system bodies. More advanced surveys are being launched with every passing decade, but not all countries have equal access to the latest technology. Space-based observatories have helped level the playing field by scanning the entire sky, but even they have their limits. WISE did map both hemispheres, but with lower sensitivity at the faint end of its detection range. There's also an emotional factor at play. In science, as in any field, people tend to look where they expect results. If most clustering of trans-Neptunian objects was first noticed in areas visible from northern latitudes, then follow-up tends to concentrate there too. We build patterns around where we've already found things. That focus reinforces itself. Some astronomers have suggested launching dedicated campaigns aimed specifically at the southern sky. These would involve scheduling telescopes in Australia, Chile, and South Africa to perform coordinated sweeps of the underexplored regions. The idea is simple. Don't rely solely on broader surveys with other priorities. Instead, aim instruments directly where the gaps have been largest. If Planet 9 is hiding down there, tucked behind a southern constellation, creeping along a near-invisible path, this might be the only way to catch it. It's also worth considering what else might be hiding in the same region. The southern sky could contain not just Planet 9, but a population of faint, slow, distant bodies that we've missed for similar reasons. Their distribution, their orbits, their interactions, they might all look different if we filled in the map properly. Right now, we're working with an incomplete picture, one shaped as much by infrastructure and geography as by cosmic design. Until that southern blind spot is closed, any conclusion about Planet 9 remains provisional. The map of the outer solar system may be as much a map of our habits and limits as it is of real celestial objects. The southern sky waits, quiet and unresolved. Maybe Planet 9 does too. Citizen science and the distributed search for Planet 9. While the search for Planet 9 has mostly been led by professional astronomers and major observatories, an important part of the story has quietly unfolded in backyards, living rooms, and small-town libraries around the world. Over the past few years, a growing number of volunteers, people without formal training in astronomy, have joined the hunt. Not with telescopes, but with their time, their attention, and their eyes. These citizen scientists are helping to comb through the overwhelming amount of data collected by sky surveys, looking for anything that might have slipped past automated systems. One of the most active and well-known efforts in this area is a project called Backyard Worlds, Planet 9. Launched in 2017 and hosted by NASA in partnership with several universities, it was designed to make use of the full sky data collected by WISE. The millions of images captured by WISE were stitched together into time-lapse sets that can be used to search for objects moving very slowly, too slowly to trigger alerts in most automated detection software. The human eye is still remarkably good at spotting faint movement, even when it's buried in noisy or imperfect images. Volunteers log into the site and are shown small image sequences, 4 frames at a time, taken years apart. Their task is to watch closely and flag anything that appears to move between frames. That motion might be tiny. It might be so subtle that a computer wouldn't catch it. But with enough eyes on the images and enough attention to detail, it can be seen. Participants are trained to look for a few different kinds of movement. Some fast-moving dots are nearby asteroids or satellites, which aren't of interest to this particular project. Others are stars that exhibit slight proper motion. But every now and then, something very slow, very faint, and possibly very far away appears to move just slightly, suggesting it could be a distant solar system object, like a brown dwarf, a distant dwarf planet, or Planet 9. The project has drawn in tens of thousands of volunteers from around the world. Some are science teachers, students, or amateur astronomers. Others are retirees, stay-at-home parents, or people who simply like the idea of being involved in real research. There's no special skill required beyond a willingness to look carefully. It's a level playing field. Every person who logs in and contributes becomes part of the same team, combing through sky images for signals that may have been missed. And the approach works. Within the first year, Backyard Worlds volunteers discovered several previously unknown brown dwarfs. These discoveries are important on their own, but they also help validate the project's method. If volunteers can find brown dwarfs hiding in WISE data, it's not unreasonable to think that other objects could be within reach as well. It just takes time, patience, and a lot of people. One of the strengths of citizen science is scale. A single astronomer or computer program can only look at so many images in a day. But thousands of volunteers, working independently from their homes, can scan through far more data than any small research team could handle alone. When the WISE dataset was released in its entirety, it was simply too large for traditional teams to study in fine detail. Citizen science allowed the search to scale up without requiring expensive new tools. For many volunteers, the chance to be part of a real scientific discovery is deeply motivating. There's the excitement of being the first to spot something strange. Each frame becomes a small mystery to solve. And in rare cases, when a volunteer flags a moving object that turns out to be something new, their contribution is acknowledged in scientific papers and databases. It becomes part of the official record. This kind of involvement changes how science is done. It breaks down the divide between researchers and the public. Rather than simply sharing results after the fact, projects like Backyard Worlds invite people into the process itself. And while Planet 9 hasn't yet been found, the possibility that someone at home, anywhere in the world, could be the first to spot it adds a new kind of energy to the search. The tools available to citizen scientists have also improved. The Backyard Worlds platform provides short tutorials, side-by-side comparisons, and real examples of what a promising detection looks like. There are discussion boards where volunteers can post strange or interesting findings, get feedback from others, and learn more about what they're seeing. These community spaces help keep the momentum going. People share tips, compare notes, and follow the progress of candidates that move up the pipeline for closer inspection. In some cases, volunteers have even helped build tools to improve the project itself. By sharing code, making tutorials, or organizing local outreach, citizen scientists have become not just helpers, but contributors to the broader scientific effort. This spirit of shared discovery has started to spread into other projects as well. While Backyard Worlds focuses on infrared sky images, other programs look for slow-moving objects in optical data or track exoplanet signals by watching for tiny dips in starlight. In each case, the core idea is the same. Human eyes, working together, can spot what machines might miss. Still, there are limits. No matter how many people are involved, the search is constrained by the data itself. If WISE didn't capture the region of sky where Planet 9 is hiding, or if the planet is too faint even for WISE, then it won't appear in the frames being studied. Likewise, if Planet 9 has a very low reflectivity, or is sitting against a crowded star field, it might be nearly impossible to pick out, no matter how sharp the viewer. As new datasets come online, there will be new opportunities to involve the public. In fact, some of these missions are already planning for large-scale participation from non-professionals. With the right platforms, people could start helping analyze fresh data just days or weeks after it's collected, scanning for objects that traditional pipelines might miss. This broadening of the search effort doesn't guarantee success, but it means the hunt for Planet 9 isn't just happening in labs or observatories. It crosses professional boundaries and taps into something simple: the human love of discovery. How Gaia could indirectly reveal a massive distant planet. The European Space Agency's Gaia mission was launched in 2013 with a simple but ambitious goal: to map the positions and motions of over 1 billion stars in our galaxy with unprecedented precision. Orbiting around the Sun-Earth Lagrange 2 or L2 point, Gaia constantly scans the sky, measuring the positions of stars over and over again across years. These measurements are so precise that Gaia can detect shifts in a star's position as small as tens of microarc seconds. tiny angles that would be like spotting the width of a human hair from hundreds of kilometers away. Gaia's main job is galactic in scale, understanding the structure and history of the Milky Way. But by capturing such fine detail in the way stars move, it can indirectly tell us something about the forces acting on our own sun. And if there's something large, hidden and massive orbiting far out in the solar system, it could be tugging ever so slightly on the sun itself. That subtle influence, in turn, would change the motion of the sun through the galaxy, and Gaia might be able to notice. This idea may sound counterintuitive at first. Why would looking at other stars help us find a planet in our own backyard? The answer lies in how gravity works at a distance. Every mass exerts a pull. The sun, orbiting the center of the Milky Way, is expected to move in a smooth path. But if there's an undiscovered object orbiting the sun from far away, that object would add a tiny extra force, changing the sun's motion just a little. Not enough to notice in day-to-day life, but just enough to matter when you're tracking stellar positions down to micro-arc-second precision. This reflex motion is the same idea used in detecting exoplanets. When a massive planet orbits a star, the star itself doesn't stay completely still. Instead, both the planet and the star orbit a common center of mass. From far away, we can sometimes see this wobble as a repeating pattern of motion. In the case of Gaia, the thought is reversed. Instead of watching a distant star wobble because of an orbiting planet, we're watching many distant stars to see if our own sun is wobbling, ever so slightly, because of something massive, like Planet 9, pulling on it from afar. This idea was explored in 2021 in a study led by Matthew Holman and colleagues. The method involves checking if there's a systematic change in the positions of background stars that can't be explained by the usual galactic rotation or parallax. If such a signal exists, it could indicate that something is subtly shifting the reference frame of the entire solar system. The accelerations we're talking about are extremely small. We're looking at motions on the order of a few centimeters per second, spread out over years or decades. But with enough data, and with Gaia's incredible sensitivity, these small nudges add up into a detectable signal. If a massive object is present, its signature could appear as a coherent distortion in the apparent movement of thousands or even millions of stars. Gaia has already released several large data sets, and each new release brings sharper accuracy. Its third major data release, in 2022, included data on over 1.8 billion stars. Future releases are expected to improve the time baseline even further, increasing sensitivity to these kinds of long-period accelerations. If Planet 9 is real and massive enough, its presence might cause the kind of slow drift in the solar system's center of mass that Gaia can eventually pick up. One of the biggest advantages of this method is that it doesn't depend on seeing the planet itself. All other searches so far, whether in visible light, infrared, or gravitational perturbation studies, have been based on detecting Planet 9's direct influence or appearance. But Gaia's approach is fundamentally different. It looks outward, not inward. It treats the stars as a vast, stable backdrop, using their apparent shifts to infer what might be happening locally. It's almost like looking at the shadows on a wall to figure out if something just moved in front of a light. There are still many challenges. For one, the expected accelerations are near the edge of Gaia's sensitivity. Detecting them requires careful filtering of noise, understanding of systematic effects, and accounting for other small forces, like the gravitational pull of passing stars or the overall tidal field of the galaxy. It's not as simple as seeing a clear wobble and drawing a line to Planet 9. The signal would be subtle and buried among many other effects that also cause stars to appear to drift over time. Another issue is the uniqueness of the signal. Even if a drift pattern is found, it might not immediately point to Planet 9. There could be multiple ways to explain such an acceleration, ranging from previously unrecognized solar system objects to more exotic ideas involving dark matter or new gravitational physics. But Planet 9 remains one of the leading candidates, especially because its predicted properties would match the kind of tug Gaia might detect. This method is still in its early stages. It will likely require the full length of Gaia's mission, which just finished in 2025, though the data is still being processed, and possibly follow-up missions with even higher precision to fully confirm or rule out such tiny accelerations. But the approach opens up a new window in the search. Even objects too faint or distant to see directly can still leave fingerprints in the sky, in the motions of stars, and in the shifting frame of reference we use to understand our place in the galaxy. In the coming years, researchers will continue digging into Gaia's dataset. Algorithms will be refined, models of solar system motion will be updated, and astronomers will look closely at the long-term accelerations hidden in the background of the stars. If Planet 9 is out there, and if it's massive enough, it may eventually reveal itself not with a bright flash in a telescope, but through a quiet and steady tug on the Sun. Using stellar occultation to detect the indirect presence, occultation studies focus on shadows, brief, tiny dips in starlight when a distant object passes directly in front of a star. For an object as elusive as Planet 9, this indirect approach offers a rare and delicate opportunity to catch it not by what it shines, but by what it hides. Stellar occultation has long been used to study small and distant objects in our solar system. Astronomers have used it to estimate the size, shape, and even the presence of atmospheres around Kuiper belt objects and asteroids. When a body passes in front of a star, even for a split second, it blocks the star's light and causes a temporary, measurable drop in brightness. The precision of this method can be astonishing. In some cases, it can detect objects too dim or small to be seen any other way. To catch such an event, astronomers must know where and when to look. Stellar occultations require careful planning, coordination, and prediction. You need to track the positions of stars with high precision and then estimate the potential orbit of the suspected object. If that predicted orbit intersects the line of sight to a star, you wait for the exact time and watch. If everything aligns, if Planet 9, wherever it may be, truly exists and crosses that narrow path, it will briefly block the star's light. The event might last only a few seconds. Because these dips are so short and so faint, they are easy to miss. This is one reason occultation studies typically rely on networks of observatories or coordinated efforts across regions. Observers at different locations along the Earth's surface can capture slightly different views of the same event. If a shadow passes over one telescope but not another, that tells you something about the object's position and size. If several observatories see the same dip in starlight at the same time, the data becomes even more valuable. The shape and depth of the light curve, how the brightness changes over time, can help reconstruct the shape of the object that caused it. In the Kuiper belt, occultations are used to study objects that are a few hundred kilometers across and relatively close by, astronomically speaking. The chance of Planet 9 passing directly in front of a star bright enough to observe from Earth is extremely small. And because we don't yet know its exact orbit, or even if it exists, it's like aiming a camera at the sky and hoping a bird flies into the frame at the perfect moment. Despite this, the concept has gained interest, especially as improvements in star catalogues make prediction more realistic. Gaia has allowed astronomers to model where stars will be, and if paired with a decent Planet 9 orbit model, it becomes possible to forecast when potential occultations might happen. Even if the chance is slim, the payoff of detecting one would be enormous. A single confirmed occultation would give us a direct measurement of Planet 9's position at that moment, its size, its location, and a better handle on its orbit. Telescopes around the world constantly monitor stars for various reasons: transiting exoplanets, supernova searches, or general variability. In all that data, buried among the noise, could be a missed occultation. An unexplained brief dip in a star's light might not have meant much at the time. But if that star lies near a proposed orbit path of Planet 9, that dip might suddenly take on new significance. Mining old data with this idea in mind is becoming part of the broader strategy. There's another interesting benefit of this method. Occultations can, in theory, detect objects that are otherwise completely invisible. This includes not only dark, icy planets with low reflectivity, but also more exotic possibilities, like black holes or ultra-cold rogue planets. Anything that blocks starlight, even briefly, can reveal its presence this way. For Planet 9, which may be too dim to see directly, this might be the only available method of detection until its location is better known. Groups like RECON, or the Research and Education Collaborative Occultation Network, work with distributed telescope networks in small towns across the western United States. They focus primarily on the Kuiper belt, but their methods could be adapted for a larger, more distant object. The key lies in coordination, having dozens or even hundreds of small observatories watching the same star field, increasing the chances of catching a rare alignment. As new tools come online, the precision of orbit models for distant solar system bodies is expected to improve. That, in turn, will refine the predictions for where occultations might occur. With better models, we'll know which stars to watch and when, turning the problem from a random search into a targeted opportunity. It is possible that Planet 9's occultation window might not occur for decades, or it might have already happened in the last few years, unseen and unrecorded. The sky is vast, the object is faint, and the timing is unforgiving. But the technique itself is sound. It's been proven again and again on smaller, nearer targets. And in a way, it's poetic, using the flicker of a distant star to reveal a hidden world that reflects almost no light at all. Could we send a probe to Planet 9? Theoretical mission architectures. Sending a probe to Planet 9 would be one of the most ambitious missions ever attempted. It would push the limits of what we currently know how to do, not just in terms of technology, but also in terms of patience, planning, and communication. This kind of mission wouldn't be like the ones that visit planets close to Earth. It would take decades, maybe even longer. But if Planet 9 is out there, and if we ever want to get close enough to study it directly, there's no substitute for going there. The first challenge would be the launch. We don't know exactly where Planet 9 is, but even the closer estimates would put it at least 400 AU away. That's about 10 times farther than Pluto. Even the Voyager probes, which have been traveling since the 1970s, haven't gone that far yet. Any mission to Planet 9 would need a carefully designed flight path to get out to those distances within a reasonable amount of time. There are a few options on the table. One is a direct launch. This means sending a spacecraft on a straight path, using the full power of a heavy-lift rocket to reach escape velocity from the Sun and head straight for the target. The problem with a direct route is that it takes a huge amount of energy. We'd need something more powerful than most of the rockets we've used before. The most likely candidate for that kind of mission, with today's technology, would be a heavy-lift vehicle like NASA's Space Launch System or SpaceX's Starship, once it's fully operational. A more practical alternative would involve gravity assists. This is the technique used by many outer solar system missions like Voyager, Cassini, and New Horizons. Instead of heading straight for the target, the spacecraft first loops around one or more planets, usually Earth, Venus, or Jupiter, to pick up speed. These gravity slingshots save fuel and allow us to reach much higher speeds than a single launch could provide. A mission to Planet 9 might use a similar trick. The probe could launch from Earth, swing past Venus or Earth again, then fly by Jupiter to pick up speed before being flung out into the outer solar system. This would require precise timing. The positions of the planets would need to line up just right, which doesn't happen very often. There might only be one good launch window every few years. Once the spacecraft is on its way, the next question is how long it would take to get there. That depends on how fast it's moving and how far Planet 9 really is. If the planet is around 600 AU away, even a fast probe traveling at 15 kilometers per second would take over 90 years to arrive. Faster speeds would help, but getting a spacecraft to move that quickly is still a major challenge. The Voyager spacecraft are only traveling at about 17 kilometers per second now, after decades of flight. Even if we manage to shorten the travel time to 40 or 50 years, using gravity assists or new propulsion technologies, we'd still face another major hurdle: communication. As the spacecraft moves farther from Earth, the signal gets weaker and weaker. Radio waves spread out over distance, and by the time they travel hundreds of AU, they become so faint that only the most sensitive receivers on Earth can detect them. NASA's Deep Space Network is currently the backbone of communication with our distant spacecraft. It includes large antennas in California, Spain, and Australia that can pick up weak signals from probes like Voyager and New Horizons. A mission to Planet 9 would rely heavily on this network, and perhaps even need upgrades or new stations to ensure constant contact. The speed of communication would also be an issue. At 600 AU, a signal would take over 80 minutes just to travel one way. That means a round-trip conversation, ask a question and get an answer, would take nearly 3 hours. Real-time control wouldn't be possible. The spacecraft would need to operate on its own most of the time, using onboard systems to navigate and handle problems. Navigation itself would be tricky. Planet 9's orbit isn't well understood. By the time the probe is launched, we might have a better idea of where it is, but even small uncertainties could add up over the years. The spacecraft would need a way to correct its course along the way. That could mean occasional engine burns to adjust its trajectory, or using onboard cameras to spot faint objects in the distance and steer accordingly. Solar panels won't work that far from the Sun. At distances beyond 10 AU, sunlight is so weak that even large panels can't generate enough electricity. The spacecraft would likely need to use radioisotope thermoelectric generators, or RTGs, like those on Voyager, Cassini, and New Horizons. These use the heat from decaying radioactive materials to generate power. They're reliable and long-lasting, but they only produce a small amount of energy, enough to run a few instruments and keep the systems alive. Given all these factors, a mission to Planet 9 would probably resemble the early interstellar missions more than the quick flybys we've done of Jupiter or Saturn. It would be a long-haul journey with very slow updates, limited data collection, and a focus on endurance. The mission plan would need to include stages for cruise, mid-course corrections, final approach, and maybe a flyby or orbital insertion if we have enough fuel and control. An orbital mission, where the spacecraft slows down and enters orbit around Planet 9, would be incredibly difficult. It would require the spacecraft to shed a huge amount of speed after traveling for decades, which means carrying extra fuel or relying on clever gravity tricks. A flyby, like what New Horizons did at Pluto, would be more realistic. It wouldn't allow for long-term study, but it would give us our first close-up images and measurements. Once there, the probe could take photos, measure the planet's atmosphere, study any moons or rings, and even map the surface. Instruments could include cameras, spectrometers, magnetometers, and particle detectors. Each one would need to be designed for extreme cold and darkness, since Planet 9 would be one of the coldest places we've ever visited. Should the mission involve a single spacecraft, or would it make sense to send multiple small probes? Could we include mini-landers or atmospheric entries if we find the planet has a thick atmosphere? Could we build in new propulsion systems, like solar sails or nuclear electric engines, to speed up the journey? These ideas are the sort of thing that will need to be explored by the mission designers. Whatever the final design looks like, one thing is certain. The mission would require patience. The people who build it might never see it arrive. The scientists who launch it might retire before the first images come back. It would be a mission that spans generations, built on the hope that the future will still care about what lies in the farthest corners of the solar system. That kind of long-term thinking is rare, but it might be the only way to reach Planet 9. How nuclear and other propulsion methods could cut the journey. Right now, most deep space missions rely on chemical rockets. These are powerful at launch, but once they're in space, they don't provide much more push. They fire for a few minutes, get the spacecraft moving, and then shut off. From that point on, the spacecraft just coasts. For nearby planets, that's good enough. But when you're aiming for hundreds of astronomical units, coasting alone takes too long. This is where nuclear propulsion starts to look attractive. There are two main kinds: nuclear thermal propulsion and nuclear electric propulsion. Both are based on using the energy from a nuclear reactor, but they work in different ways. Nuclear thermal propulsion is the simpler of the two. It works by using a nuclear reactor to heat up a gas, usually hydrogen, and then shooting that gas out the back of the spacecraft to create thrust. Because nuclear energy is so dense, this method can deliver a lot more push than chemical engines. It also allows the spacecraft to carry less fuel, since the efficiency is much higher. The idea has been tested before. Back in the 1960s and 70s, the US ran a program called NERVA that built and fired real nuclear thermal engines. They never flew in space, but the tests showed that this kind of engine could work. If used today, a nuclear thermal rocket could cut travel time to Planet 9 by a large margin. Instead of taking 70 or 80 years, a spacecraft might make the journey in 30 or 40. That's still a long time, but it's within a human lifetime. A mission could be launched, tracked, and eventually analyzed by the same generation of scientists who built it. Nuclear electric propulsion works a little differently. Instead of heating a gas directly, the reactor generates electricity. That electricity then powers an ion engine, a device that slowly pushes out a stream of charged particles to create thrust. The force is very gentle, but because it runs continuously for years, the spacecraft can build up a lot of speed over time. NASA's Dawn mission, which visited Vesta and Ceres, used ion propulsion powered by solar panels. A nuclear-powered version could go much farther and faster. A nuclear electric spacecraft could adjust its path mid-flight, steer toward interesting targets, and even slow down near Planet 9 to conduct long-term studies. The main drawback is that the engines are slow to get started. They don't give the big boost that's needed to leave Earth quickly. So they'd need to be combined with other launch systems to get out of Earth's gravity and into space. That brings us to the second major tool: gravity assists. When a spacecraft flies close to a planet, it can steal a bit of that planet's motion through a carefully planned swing-by. The result is a boost in speed and a change in direction, effectively acting as free fuel. The key is timing. The planets have to be in the right spots at the right time for a gravity assist to work. That's why missions often have narrow launch windows. If you miss the window, you have to wait years for the alignment to happen again. Voyager 2, for example, used a rare planetary alignment in the late 1970s to visit Jupiter, Saturn, Uranus, and Neptune, all in one trip. Each flyby gave it more speed and helped it reach the outer planets in less than 12 years. The trick is to figure out the sequence: which planets to use, when to launch, how close to fly by. All of this would need to be calculated in detail years in advance. Engineers would use complex simulations to plan the path. The goal would be to reach a balance between speed, fuel use, and scientific opportunities. And of course, the final leg of the trip would depend on having a good estimate of where Planet 9 is. There are also more exotic propulsion ideas under study. One of them is solar sails. These use large, lightweight sheets that catch the pressure of sunlight to slowly accelerate. They don't require fuel, and once deployed, they can keep moving faster and faster. A solar sail mission might take longer to get going, but once in deep space, it could cruise at high speeds indefinitely. Another concept is nuclear pulse propulsion, where small nuclear explosions are used to push a spacecraft forward in tiny steps. This idea has been around since the Project Orion days of the 1950s, but it's never been tested due to safety and political concerns. Still, even without these futuristic systems, the combination of gravity assists and modern nuclear engines could make a mission to Planet 9 realistic. The spacecraft would still need to be built to survive decades in the harsh environment of space. It would need to be smart enough to handle its own navigation, corrections, and data collection far from Earth. The mission team would need long-term funding, and a support structure that could keep the project going through many phases. But the payoff would be huge. We'd finally get a close-up look at a world that's been hidden in the darkness for billions of years. We'd learn what it's made of, whether it has moons or rings, and how it fits into the larger story of the solar system. Starshot technologies. Could a light sail catch up to Planet 9? In recent years, some of the most forward-looking minds in space exploration have begun thinking differently about how we send spacecraft into deep space. Instead of building bigger rockets or more powerful nuclear engines, they're asking a more radical question. What if we made the spacecraft smaller, much smaller, and instead of carrying its own fuel, what if we pushed it with light? That's the basic idea behind beamed light sail technology, something being studied seriously through projects like Breakthrough Starshot. It's an approach that's very different from traditional spaceflight. Instead of launching a heavy probe with tanks of fuel and a big engine, the spacecraft is a tiny chip attached to a thin, reflective sail. The sail doesn't push itself. Instead, a powerful laser based on Earth, or possibly on the Moon, fires a beam of concentrated light at the sail. The light particles, or photons, don't have mass, but they do have momentum. When they strike the sail, they push on it, just a little at first, but with constant pressure over time. If the sail is light enough and the laser strong enough, the result is a burst of rapid acceleration. Breakthrough Starshot's goal is to send small probes to nearby stars, like Proxima Centauri, within a human lifetime. The speeds involved would be staggering, up to 20% of the speed of light. At that pace, a probe could reach Alpha Centauri in just over 20 years. For a world inside our own solar system like Planet 9, such a system wouldn't need to go nearly that fast. But the technology might still offer a path to exploring the distant outer regions of the solar system far faster than anything we can launch today. There are advantages to this method. The most obvious is speed. A light sail, if it works as planned, could reach extreme velocities in a matter of minutes or hours after launch. There's no need to carry fuel and no need for multiple stages. That makes the spacecraft far less massive and far simpler. You don't need to worry about engine failures or fuel line problems. Once the sail is deployed and the laser hits it, acceleration begins. A light sail probe could arrive at Planet 9 in just a few years instead of decades. If the craft could reach 1% of the speed of light, about 3,000 kilometers per second, it could cover 600 AU in a little over 3 years. Even if it traveled slower, say a few hundred kilometers per second, it would still arrive far faster than current or near-future nuclear or chemical missions. But there are big trade-offs. One of the most serious is payload. These probes would have to be tiny, only a few grams in mass. That means you can't carry much in the way of instruments. Forget about spectrometers, large cameras, or sample collectors. Instead, you'd be limited to very small, low-power sensors. Maybe a tiny camera, a basic magnetometer, or a temperature probe. The craft would also need to include a communication system, a power source, and navigation equipment, all squeezed into a space smaller than a smartphone. Another issue is aiming. At those speeds, a tiny error in the launch angle could cause the spacecraft to miss its target by millions of kilometers. Planet 9 is already hard to find. Sending a light sail probe to hit a specific point in space years later would require extremely precise predictions and aiming. Then there's the problem of deceleration. Light sail technology is great for speeding up, but slowing down is much harder. Once the sail reaches its cruising speed, it has no way to stop or even slow down unless it uses external forces. For a star mission, that's fine. The probe just flies by and sends back whatever data it can. But for a solar system target, especially a cold and dark one like Planet 9, scientists might prefer a slower approach to allow for more detailed study. Some ideas have been proposed to address this. One option is to design the light sail to reflect sunlight in a way that naturally slows it down as it moves farther from the sun. But at the distances we're talking about, sunlight is incredibly weak. Another suggestion is to use a second laser system, placed somewhere farther out in the solar system, to reverse the acceleration and help brake the craft. That would be a massive engineering challenge, requiring not just one, but two high-powered laser arrays in space or on distant planetary bodies. Powering the sail itself is also a concern. The energy needed to accelerate a light sail to even a fraction of the speed of light is enormous. The breakthrough Starshot concept imagines using a ground-based array of lasers totaling 100 gigawatts, roughly the combined output of hundreds of nuclear power plants, focused onto a sail for a few minutes. That kind of infrastructure doesn't exist yet, and building it would take years of development and international coordination. The sail itself also needs to be extremely light and strong. Materials like graphene and other nanostructured films have been suggested, but these are still in experimental stages. The sail must be able to withstand the intense heat and pressure of the laser beam without tearing or vaporizing, and once it's in space, it needs to remain stable and correctly oriented, using very limited onboard control systems. Even with all those challenges, light sail probes offer something that other missions don't: the chance to test multiple paths at once. Because each probe is small and relatively cheap, it's possible to send out dozens or even hundreds of them, each with slightly different trajectories. Some might aim for where Planet 9 is thought to be. Others could fan out and explore nearby areas. If even one or two succeed in flying by the planet and sending back a few images or measurements, the mission could be considered a breakthrough. This kind of swarm approach changes how space exploration could be done. Instead of relying on one large, expensive spacecraft with decades of development behind it, we might send out fleets of tiny explorers, knowing that most will fail or miss their targets, but a few might succeed spectacularly. That's very different from the traditional model used by NASA or ESA, but it's an idea gaining traction in the private sector and among forward-thinking scientists. Would Planet 9 even be a safe place to visit or orbit? The challenges of deep space at hundreds of AU are extreme and unfamiliar, and while the planet itself might be the main target, it's everything surrounding it that would make or break a mission. At those distances, the solar wind is drastically weaker than anything spacecraft have dealt with so far. The solar wind is the constant stream of charged particles emitted by the sun. Closer in, it's responsible for pushing on spacecraft, shaping magnetic fields, and even creating communications interference. But out at the edge of the heliosphere, the solar wind slows, thins, and loses pressure. By the time it reaches the theoretical orbit of Planet 9, it's barely a whisper. For a spacecraft, that reduced solar wind might seem like a good thing: less interference, fewer charged particles. But the opposite could also be true. The solar wind, when strong, helps form a kind of protective bubble around the solar system called the heliosphere. This bubble shields inner regions from high-energy galactic cosmic rays coming from deep space. Once you get beyond the strong protection of the inner solar system, the background radiation environment actually gets harsher. Voyager 1 and Voyager 2 have already passed beyond the heliopause, the outer edge of the solar bubble. Instruments on board showed that the flux of high-energy particles increases dramatically once that boundary is crossed. These galactic cosmic rays are more penetrating than the solar wind, and they can damage electronic components, memory units, and other sensitive systems. While Planet 9's predicted orbit likely keeps it within the heliosphere most of the time, its position near the outer boundary could mean exposure to higher doses of background cosmic radiation. Spacecraft operating near Planet 9 would need shielding far beyond what's used for satellites in Earth orbit, or even probes like Juno or Cassini. In previous deep space missions, engineers have added thick layers of aluminum or used specially designed radiation-hardened chips. But at 600 AU, the long-term exposure could accumulate damage over time. That makes mission duration a factor. A quick flyby lasting hours or days might not be heavily affected, but an orbiter that remains nearby for months or years would need to withstand a much more punishing environment. Temperatures also hover just above absolute zero, No known object in the solar system is colder than the ambient deep space out there. Spacecraft electronics usually generate a bit of internal heat, which helps, but long-term systems like batteries and fluid lines can freeze if not properly insulated. For missions to Jupiter or Saturn, engineers have used heaters powered by onboard energy sources. For outer solar system targets like Pluto, the New Horizons mission relied on a RTG to provide steady heat and power. Any probe sent to Planet 9 would almost certainly need an RTG too, but RTGs come with weight and complexity, and they must be designed to survive launch accidents and long-duration travel. If Planet 9 has rings, a moon system, or even a faint atmosphere, those could pose risks to orbiters. Dust particles, even tiny ones, can be deadly at high speeds. New Horizons had to fly through Pluto's system carefully, watching for debris. Cassini eventually dove through Saturn's rings and survived, but only after years of planning and protective maneuvers. If Planet 9 is a gas giant, it may have a strong magnetic field like Jupiter. That could influence how radiation is trapped near the planet and how it affects spacecraft electronics. A strong field could also interfere with navigation systems or scientific instruments if not accounted for. On the other hand, if Planet 9 is more like a large rocky super-Earth, it may have little to no magnetic field, leaving orbiting spacecraft fully exposed to space radiation. Orbital stability is another question. The planet's gravity could be weak compared to the Sun's pull at that distance. This means any spacecraft trying to orbit Planet 9 would need to do so carefully. A weak gravity field also means slower orbital velocities and longer orbital periods, which can affect how much data the probe can gather in a given time. Maintaining a stable orbit could require small course corrections, and without sunlight for solar power, those maneuvers would need to be minimal to conserve onboard fuel. Surviving near Planet 9 isn't just a matter of getting there. It's about designing a spacecraft that can function in the coldest, loneliest corner of our solar system, surrounded by radiation, darkness, and delay. Every part, from the antenna to the processor to the battery, has to be built for endurance, not just against temperature or speed, but against time itself. Science goals for a Planet 9 mission beyond just proof. If a spacecraft ever reaches Planet 9, the job won't end with just proving it's there. In many ways, the real science would only begin once the spacecraft is in its vicinity. The planet's existence may solve a long-standing mystery in orbital mechanics, but uncovering its physical nature could open up entirely new questions about how our solar system formed and what else might be hiding at its edges. That's why any mission designed to visit Planet 9 would need to be an observatory in motion, sent not just to see, but to measure and decode. One of the first things scientists would want to determine is the planet's mass with as much accuracy as possible. From Earth, mass can only be estimated indirectly, through the gravitational pull Planet 9 might exert on other objects, like the distant Kuiper belt bodies. But up close, a spacecraft can map the gravitational field by tracking how its own path is influenced as it moves through the planet's space. The tiny deviations in trajectory, if measured carefully, can reveal not just total mass, but even the internal mass distribution. If the planet is lopsided or has a dense core with a lighter outer shell, the spacecraft's orbit will wobble slightly in response. Knowing the mass allows scientists to make sense of everything else. A high mass could mean it's a gas giant, maybe a shrunken version of Uranus or Neptune. A lower mass might suggest a rocky super-Earth, a planet type common around other stars, but not yet confirmed in our own solar system. The structure and layering of the planet, how much is rock, how much is ice or gas, could depend on how massive it is and where it formed in the early solar system. Closely tied to mass is the planet's size, and from that, its density. A spacecraft could determine this by imaging the planet from a known distance and comparing that visual size with the gravitational measurements. High density would suggest a rocky body. Low density could point to a thick gas envelope. If it's mostly hydrogen and helium, that would imply it formed closer to the Sun and was later flung outward. If it's mostly ices or rock, it may have formed in place. perhaps representing a building block of the outer solar system that never grew large enough to become a gas giant. Spectrometers aboard the spacecraft could scan the planet in various wavelengths to detect what chemicals are present. If the planet has an atmosphere, even a thin one, it could reveal signs of methane, nitrogen, water vapor, or exotic gases like ammonia. These clues could hint at similarities to Neptune, Titan, or even dwarf planets like Pluto. An icy crust might reflect sunlight in very specific patterns. A darker surface, possibly covered with organic tholins like those seen on outer moons, would absorb more light and appear less reflective. Beyond the planet itself, scientists would want to scan its surroundings for rings or satellites. Both Uranus and Neptune have faint ring systems, and if Planet 9 has rings, they might be similarly faint and narrow, detectable only with sensitive imaging tools. Their shape and orientation could reveal information about the planet's spin axis and history of impacts or gravitational interactions. Moons could range from small captured rocks to substantial bodies with their own geological histories. A moon could even act as a probe of the planet's mass, just as Earth's moon helped determine our planet's own properties. The orbits of any moons would give more clues to how the planet formed and whether it interacted violently with other solar system objects in the past. If Planet 9 has a magnetic field, instruments like magnetometers could detect its strength, orientation, and how it changes over time. A strong field might suggest a molten, conductive core, like those seen in Earth, Jupiter, or Mercury. A weak or absent field could mean a frozen core, or a planet that has cooled over billions of years. The way the field interacts with the solar wind could even create a bow shock or tail, like we see around the gas giants. Some of the most subtle science would come from monitoring the space environment near Planet 9. Dust detectors, for example, could tell us whether the planet is embedded in a larger disk or debris cloud. Tiny particles might pepper the spacecraft, offering direct samples of the outer solar system's building blocks. Instruments could also scan for energetic particles, plasma interactions, or changes in the solar wind that behave differently at these remote distances. Temperature readings across the planet's surface or cloud tops could reveal internal heat. Some planets, like Jupiter and Saturn, emit more energy than they receive from the Sun. If Planet 9 has a warm core or is still cooling from formation, it might glow faintly in the infrared, something that onboard instruments could detect even in the total darkness of its orbit. If there are variations in temperature, poles colder than the equator, or spots that are unexpectedly warm, it could suggest weather, cloud patterns, or even internal activity. Gravity science could be used to search whether Planet 9 has a differentiated interior. That means seeing if it has a distinct core, mantle, and crust. Variations in gravity, especially when the spacecraft flies low or in an elliptical orbit, can paint a kind of 3D picture of the planet's interior, even without drilling into it. Combined with magnetism and heat data, this picture can help scientists decide whether the planet formed like a terrestrial body or like a mini gas giant. Such a mission could also look outward. From this distant perch, far from the glare of the inner solar system, a probe could make unique observations of the Milky Way, background stars, or even the heliosphere's shape. Though not directly related to Planet 9, these secondary observations could be bonus science, helping us understand how the Sun's bubble looks from the outside. And finally, there's the question of time. A probe near Planet 9 could be used to monitor the system over months or even years. Do storms form on the planet? Do any moons show volcanic activity or seasonal changes? How stable are any ring structures? Long-term observation lets scientists catch things in motion, not just take snapshots. Just like we've learned new things from years of watching Saturn with Cassini, a dedicated orbiting mission to Planet 9 could uncover unexpected dynamics. Planet 9 could turn out to be a fossil from the earliest days of the solar system, or it might be something else entirely, a kind of world we didn't even know was possible. Either way, once we find it, the next step isn't to stop, but to study it in depth as a world all its own. What would the existence of Planet 9 mean for planet formation models? For a long time, scientists believed they had a solid grasp on the general process of planet formation. A cloud of gas and dust surrounds a young star, and over time, tiny particles in that disk stick together. Through collisions and clumping, those particles grow larger. Eventually, they become planetesimals, chunks of rock or ice a few kilometers across. If those planetesimals are in the right region of the disk and manage to avoid being broken apart, they can grow into planets. This idea, called core accretion, has been the main explanation for how Earth, Jupiter, and the other planets came to be. But this model mostly describes what happens within about 30 AU of the Sun, or roughly the distance out to Neptune. Beyond that range, things get trickier. The density of material in the protoplanetary disk drops off sharply. There's simply not as much gas and dust that far out. That makes it harder for objects to grow big. Even if clumping starts, it's slow. The particles are fewer, the collisions are rare, and the whole process can take longer than the disk itself survives. Most disks around young stars only last a few million years. That doesn't leave much time to form a planet 5 to 10 times the mass of Earth way out at 500 AU or more. So if Planet 9 is out there, either our understanding of disk structure is wrong, or something unusual happened during the solar system's youth. One possibility is that the outer part of the solar system's disk was much more massive than current models suggest. If the disk extended far beyond Neptune and retained a decent amount of solid material, perhaps there was enough raw material at great distances to slowly build a super-Earth. But to support that idea, scientists would need to revise models of how material in disks spreads and clumps under the influence of the Sun's gravity and the early solar wind. It would mean rethinking how quickly the disk dissipated and what mechanisms could concentrate material far from the center. Another option is that Planet 9 formed closer in, perhaps somewhere near the region of the giant planets, and was later flung outward. Many formation models already include a period of migration and chaos in the early solar system. Jupiter and Saturn, for example, are thought to have moved from their birthplaces. Their gravitational tugs disrupted smaller objects and could have even rearranged the orbits of Uranus and Neptune. This early period of shifting orbits, sometimes called the NICE model, paints a picture of the solar system as a very dynamic place in its first few 100 million years. Most previous models assumed that large planets either got tossed into the Sun or ejected from the solar system entirely. Having one survive in a stable, distant orbit would mean we've underestimated the likelihood of soft ejections, where a planet is pushed outward but not lost. Yet another possibility involves what's called gravitational instability. This is a different formation model from core accretion. Instead of growing from small bits of rock and ice, a planet might form when part of the disk itself collapses under its own gravity, like a miniature version of how stars form. This process is fast. It can happen in just thousands of years, but it requires very specific conditions. The disk has to be massive and cool enough for large clumps to form and hold together. Gravitational instability is often invoked to explain the formation of massive gas giants like Jupiter in distant exoplanet systems. If Planet 9 formed this way, it would push astronomers to consider that such mechanisms might operate in our own system too, not just around other stars. If Planet 9 formed far out through core accretion, then other star systems might have similar distant giants. If it was flung there by gravitational chaos, then we might expect more rogue planets drifting through interstellar space. If it was stolen from another star, it would suggest that planet sharing is more common than we thought. And if it formed from gravitational instability, it would reopen debates about which mechanisms are dominant in building planets. Planet 9 could act as a bridge, connecting what we know about our own solar system to what we see in others. It would give astronomers a local example of a planet type that seems common elsewhere, but has always been missing from home. And just like the discovery of Neptune helped refine Newton's laws, the detection of Planet 9 would force us to fine-tune the rules of planetary formation and migration. It would be a challenge, but also an opportunity. to update our models, test new ideas, and get closer to understanding how planetary systems, including our own, come together from clouds of dust and gas. What do you think are the odds of this long sought-after planet truly existing? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.